Hey guys, this is going to be the gym term 1A walkthrough. Um, Hopefully you guys are studying very hard this week. I know your exams on Thursday, and I imagine a lot of you are worried given the limited amount of practice, which is why I wrote the 4 practice exams to open up the amount of practice you guys have, especially exam-like practice, right? So if you took a look through 1A, right, this is, and even the other ones, right, this is typically what you see, some kind of nomenclature vocab mess in the front, usually about 8 up to 8 predicted products, and then mechanism question where you predict the product and then do the mechanism. There's 2 sentences on these, but there's usually only 1. I just did 2, so you get extra practice. Extra practice doesn't hurt. And sometimes there are 2 if they're really short, like if they're like 2 short ones, like 3-4 steps, you usually get 2 of them. But I just put 2 on here just give extra practice. And NMR, right? So this is the usual makeup of the exam. I know this looks nothing like the practice. The practice is a bit outdated. This is a bit more, in style, the new way to write these. Okay, cool. So aim of this video, 1 is to get through, the exam and talk about, strategies and what are the concepts you need to know to answer a question, and if it's asked again, how could it be asked and what to know about it. We'll also talk about if you're only given 1 practice exam, right, how do we expand it to a couple, right? Like how do we take these problems and make them even better for us? Because imagine if before the next midterm I get hit by a bus or something, I'm out of commission for the rest of my life. You'll have to make do without me writing these, so you'll need something to help generate your own problems and do your best. So we'll talk about that. Okay. NMR, we'll just talk about, usually with these NMRs, there's like some kind of strategy, some kind of peaks you have to know, and you'll be able to do them. Okay, cool. All right. Now with this first video, I actually wanted to do a little bit of review because, if you don't know your reactions, there's no way you can solve any of these, right? And it's not going to be very helpful if I just walk through this and you don't know anything. So we'll spend about the first hour talking reactions, mostly focus on reactions, and then we'll when we get to mechanism, we'll talk a little bit about mechanisms, and then when we get to synthesis, we'll talk a little bit about synthesis tips. So expect this video to be about 2.5 hours probably, but I'll say that if if you're completely lost, you don't know what you're doing, these 2.5 hours will probably be the most important 2.5 hours of your life, because we'll get you from that F to at least a C, right? If you do the rest of practice exams, you can get up to like a B probably. Okay. The gym guarantee is that I can get you to a C for sure, though. If you're going to this like I haven't studied at all, right? I understand nothing in lecture. I've done absolutely nothing, right? I can definitely get you to a C. Getting into that BA range is going to require a little more practice on your own end, but it's totally possible. Okay, cool. So without further ado, right, with not much else left to say, let's just get into the review. Let's talk about the material. I'll focus mainly on reactions. Mechanisms we'll talk about when we get to mechanisms, but we'll focus mainly on reactions right now, and what you need to know, right? What are some tips and tricks and some cool examples? Okay. Now, actually, before we even get into this, one thing I will say is that I've shared a couple of docs. For example, the review docs, right? I've shared this one and this one. These are meant to prepare you in seeing transformations and whatnot, and what you need to know. It's also preparing you to organize. One of the biggest things in this class is you have to learn how to organize material, right? On paper, there's 100 reactions, but actually there's only 4, right? Because they all fit into the same kind of mold, right? I guess there was some I forgot about. I think the H2 and something else, but I mean, yeah, like there are some, and you don't have to know this because this wasn't covered in this class, but in essence, right, we can take all these mechanisms, all these reactions, kind of condense them into a couple. They make our life a million times easier. Okay, so I know there's a lot of material, but you have to find the patterns and clump them together. Otherwise, you're going to be stuck practicing a million reactions when only there's like 3, right? Not really 3, but you get my point. Okay, so that's the point of these review docs, right? Is to kind of help you condense that material and help you out. There are some problems at the end of these. Don't worry, these are not indicative of what you'll get in the exam. These are just challenge problems. They're exactly that. They're challenges. They're hard. They're not easy. So don't worry if you look at these and you're like, oh my God, what in the world am I supposed to know this? Not really. I wrote really fun problems just to write them. Okay. There's also this E2 one. I don't remember if I sent this. I'll send it again. But yeah, so it's the point of these review docs is to kind of help you out. Okay. So if you want, you can have this pulled up and follow through while we're going through the review while you're writing your notes or whatever. That might be useful. Okay, cool. Let's get into the review. So 118b begins with the study of the alkene, right? The pi bond. And much like the epoxide from 118a, right? Both of these functionalities, share in that they cross over 2 carbons, right? They're across 2 carbons. And so the idea of that vicinal difunctionality, if those of you guys remember, I made a big deal about this back in 118A. Same deal here. Having this functionality across 2 carbons gives us access to vicinal difunctionalities, or allows us to at least, talk about functionalizing one carbon over the other, right? Or having functionalities on those carbons. So a lot of the reactions we'll see will cover, or at the very least, will do something about the vicinality of the pi bond. And it's a great way of figuring out what to do in synthesis, or, what to do in general when it comes to alkene problems. But before we even talk about vicinal difunctionality and the reactions and whatnot, right, we have to understand how to make pi bonds as well. Okay. And so this is actually something, I mean, we've talked about this in 118A, right? But making pi bonds is fairly simple, right? You just got to eliminate, right? So if I want to, oops, not that. If I want to make this pi bond here, I just got to eliminate. I got to do like an E2 type reaction. That's the most reliable reaction to make a pi bond, right? As of right now, at least the most reliable reaction, right? Do an elimination type reaction. So whenever you see an alkoxide, very good cue in this class for this first midterm, you're trying to make some kind of alkene, because alkoxides are strong bases, right? And bases are what are initiating the mechanism, right? Which, again, to go very quickly, right? Mechanism usually is if we have this alpha carbon that holds the bromide, we have this beta carbon next door, we're eliminating a proton from the beta carbon, right? To form an alpha beta double bond. Okay, so all E2s are beta eliminations. So it can always help to label your beta carbons, especially, I mean, in this case, we only have 1, but imagine if there was a case where I had 2, right? 2 beta carbons, right? Remember, alpha, and then anything that's just alpha is beta, so beta 1, beta 2. In this case, they're both equal, so it's a matter of who I like more, right? Do I like left or right more? I think I like left more in this case, so let's go ahead and eliminate across that. But I can use, some kind of strong base, right? Again, using that alkoxide strong base and get out an alkene, okay? Now, in this case here, where it's primary, right, it's actually better to use a bulkier base, actually. But in these more bulkier substrates, secondary, down, it's just, you can use whatever base you want. Again, alkoxide is your key. So you see alkoxide on this exam, think elimination. I've got to do some kind of elimination, okay? Another type of bulky base is LDA, okay? So I look for a beta carbon and I just eliminate across that, right? Pretty simple, right? In the case of these, terminal, it's not too hard to figure out what to do, right? It's not too terrible. Where things get a little trickier though is when I have, right, differing beta carbons. Right now I have a HA and a HB, where HA is more sub and HB is less sub, right? Is there any way that I can inspire some selectivity here, right? Can I get a base to attack one over the other? And the answer is yeah, right? HA, the more sub, use a small base. So we'll call this the SSB, the small base, right? Get out this alkene here, right? Technically, there are 2 hydrogens here, so we'll talk about this in a second. But HB, if I want to attack that, use a bulkier base, right? So I get this here. So we have names for this, right? We call this a Zaitsev, we call this the Hoffman, but this is how we inspire some selectivity, right? Is we have these 2 different beta hydrogens, and we're able to attack one over the other based on the base size that we have. So seeing these can, start to associate these differences. Okay. Now HA technically has 2 of these hydrogens here, HA and HB, and HA and HB, right? HA would give us, for example, this trans alkene. HB would give us this cis alkene. Generally speaking, trans is more stable than cis. So usually in elimination reactions, we tend to get more trans product than cis product. So I wouldn't really stress too much on the front of, do I have to write both? No, not really. Only the trans will be fine. Okay. So anytime your beta carbon is a CH2, right? Your beta is a CH2. You can have cis trans isomers, but typically you only get the trans isomer. Okay. When your beta carbon is a CH3, right? You got a terminal alkene, right? So who cares? They're all going to be the same regardless of which H you take off. So who cares? Okay. Technically 3 products, but they're all the same. Okay, cool. So elimination is pretty simple, right? You can have 1 beta carbon eliminated across that, super simple. You can have 2 if they're identical, who cares? But if there's not identicalness, if there's a difference, right, we can motivate one position to be attacked over the other. So how do I increase the complexity? Well, let's say that I have a tertiary center, right? Again, now I only have 1 hydrogen, but that tertiary center is chiral, right? Now with the chirality at play, right, we have a bit more, subtlety and nuance in how do we answer the question. Okay. So E2 formally, yes, it is a beta elimination, but formally it's an anti-elimination. And what that means is that the leaving group, so in this case, the bromine, and the beta hydrogen, the H beta, as I'll put here, they've got to be anti to each other. They've got to be trans. Okay. And so the easiest way to see that is when H and Br, right, one is dash, one is wedge, right? That's an easy way to see it. So in this case, right, the elimination, this is in the anti transition state. So the alkene that I see, or the confirmation I see, that's going to be the alkene that I make, right? And so you can see this here would be the Z alkene because the ethyl and the methyl here are on the same side, right? I never see formation of the E alkene, right? So this is the stereospecificity of E2, right? You can make terminals however many you want. You can make cis and trans, but you can't make E and Z. You only make E or Z. In this case, we're going to make the Z alkene. Okay. So in a case like this, it's pretty simple, right? You just got to get rid of the H and get rid of the Br, and what you see is what you get, right? For the most part, because it's already anti, so that's great, right? But what happens if I have a substrate that's not anti? So let's say that I have, this H beta here is still, dash, but let's say I take the diastereomer of this and do this, right? No longer is this anti. Well, I mean, obviously you can't do elimination here. You do small base here, by the way, right? It's not anti. So, we've got to do some kind of rotation here, okay? So you got to get comfortable with this. I would just recommend doing practice problems. It's easy to write them. You can write them on your own. But you just got to do a little bit of rotations, right? So we want H, I'll rotate on this center here. You can rotate here too, but I'm just going to choose to do this one because I have everything drawn out. But HB is going to rotate to the wedge for it to be useful, right? Or we need it we need it as a wedge, so to be opposite to BR. And so the wedge will go to the plane, and then the plane will go to the dash, right? You want to make sure your arrows go in sort of a line, right? Like imagine if you did this, if you said this goes here and this goes here, that's not going to make sense. They're opposing directions, right? So we've kind of got to go in a circle here. Yeah, make sure that works out. Okay, cool. But anyways, we can do our rotations. I'll reset, that, or I'll set up that chiral center there. Again, HB goes to the front there to be opposite to BR. Methyl will go to the plane, so we'll go here. I'll write out CH3. And then we'll have the ethyl in the plane. Okay, and now we can do our elimination, right? We can go ahead and eliminate out the Br and the H here. And what we'll get, again, in the plane is going to be the methyl and the ethyl, so we can draw the pi bond like that. All that's left is the CH3 and the H that's on that bromine carbon, right? And so now we get the E isomer, right, over the Z isomer. Okay, cool. So this is how elimination get a little more complex, right? You have to consider the anti-periplanarity of the molecule, but it's not too bad. Usually if there's an E2 question, it'll be something like this. Maybe it might be littered with a bunch of like functionalities, but don't worry, right? Just, focus on the anti-periplanarness, right? And you'll be fine. Okay. Now, there is a little bit of a trick you can do here. It works about 90% of the time. I'm sure that someone could think of an example where this wouldn't work. But one cool thing you can do is, so here, I mean, they're syn to each other. Whenever they're syn to each other, so the H and the Br, they're syn to each other, what you can do is you can draw the alkene that results from this elimination. If it were to eliminate like this. Now, again, obviously this is wrong. This can't work, right? Because we just saw, I mean, again, this is anti, so it's not going to work. But we also just saw that this Z alkene belongs to the other diastereomer. So what you can do is you can purposely draw the wrong diastereomer, so in this case E, and then just turn it into the Z isomer, right? Like flip the isomer, right? Turn it from E to Z or Z to E, whatever you need to do, right? In this case, that would mean, like, for example, turning this methyl up here, right? You can also, turn this into an ethyl and a methyl and keep this the same, right? Whatever you gotta do to make it Z, just flip it, right? So that's a little trick you can do. It works about 90% of the time. It always works if they are syn. So Br and H are syn. If they're both dash or both wedge, that trick always works. But I'm aware of some instances where that's not gonna work. So that's a cool little trick you can use if you want to. Okay, cool. So let's do one more of these just to, again, it doesn't hurt to do a little bit of practice on this. Right, there's only so many ways you can write this question, right, before it just kind of gets overdone. But let's say we had this and we had, the usual setup of the alkoxide and its alkanol solvent, right? Again, Br and H are not anti to each other, right? And they're also not cis to each other, so I'm not confident using the trick, but I can do a little rotation here. I'll use a different color just so it stands out. But H, so Br is a wedge, so I want H to be a dash. Dash will go to wedge, and then wedge will go to plane. Right, so this center here will stay the same. Right, and then, right, I'll just set this center again, right? We want H to be here, and that's where it went. I'll put a CH3 here so we can track that over here, right? This can go to the plane, and then the ethyl came into the front. Now I can do my elimination, super easy peasy, right? Nothing to worry about. One little trick you can use to write out these problems if you're having hard with that time with them is just use relative stereochemistry. So let's say I wasn't sure how to translate this into alkene. If I ignore the Br and the H, what I notice is that sorry, this should be a dash, so ugly drawn. I noticed that the ethyl and the methyl are trans to each other. One's wedge, one's dash. So if methyl were here, ethyl would have to be here. Only thing left is to put the ring and then the CH3 onto here. Okay, so that's one way you can do that if you're having a hard time with that. Okay, cool. Now, always look at your base just really quickly, because imagine if this was instead, a bulky base. Always label your beta carbons too. Right, so remember, this is alpha because it holds the bromine. Anything attached to this alpha is going to be beta. So this would be beta. Oops, sorry. This would be beta. This would be beta. This would be beta. Right. If I use LDA as a bulky base, it wants the least substituted position. Right. We just want to attack right there, and our life is super easy. So my biggest piece of advice is just look at betas, because or look at your base and then look at your betas, right? Because maybe the base might even just not even be something that's complicated. Might even just want to make that. So you're like wasting time to do something you don't have to do. Okay, cool. All right. Only thing we'll talk about left on the E2 front is just the idea of rings. Rings make E2 a little more difficult because rings are not able to rotate like linear chains are. So everything is very specific on a ring, right? Whether you have anti or not is always an absolute. You can't just rotate to make something that's not anti-anti. So when we're doing this problem here, I highly recommend the first thing you do is you just figure out, okay, do I have anti-protons on every beta carbon, right? So in this case, right, this is my alpha, so these are my betas, right? Do I have anti-protons? In this case, yes, I do, right? I have anti-proton here, anti-proton here. So there's a way to discriminate between them. If I call this A and B, right? HA is the more sub, so I'll use a small base. HB is a less sub, so I'll use a stronger, bulkier base, right? And so I can get two different alkenes out of this, right? Because both sides, both sides have protons I can eliminate. One big thing, don't forget, I see people do this every year. Don't draw this. Don't put that stereochemistry on that, right? If there's anything on an alkene, it should be flat. It has to be planar with the alkene. Okay, don't do this. Your TA will laugh while they take away your points. Okay, true story right away. Cool. So again, if there is a side where we have protons, right, we could consider it. But let's say that I did the diastereomer of this where Br is actually a dash, right? And I reconsider this problem, right? Now, when I think about, okay, HA and HB, do I have antiprotons on both sides? Turns out I don't anymore, right? HA is no longer anti. So HA is no longer allowed. So whether I use a small base or a big base, does not matter. I will always form this alkene here. Okay, so this is the trick of E2. This is the trick of E2, right? So look out for that. Okay, common trick questions you might see is something like this, right? Where you have this here, right? This is clearly going to be, this is one of our first NR problems ever in this class. And when you have something like this, doesn't matter if it's this or this, right? It's never going to eliminate, right? Both these hydrogens are anti. A trick question that I wrote on the midterm 4 that I'm okay with spoiling here, because I'm not sure how many of you guys will actually even do that one, is this one here. People kind of instinctively, when they see a base here, instinctively just go with NR because they think of this problem here, where we see H and H here, they're both syn, right? So the H's there are both syn, right? And so people instinctively think this is the same. But remember the trick, always label your betas. This is alpha, so beta, beta, and beta. So yes, these betas don't count, right? Because they're in the ring and they're syn. But this is outside the ring. This can be anti at any point in time. So actually, this is not NR. This actually has an answer. Okay, this is also in that E2 doc, by the way. So it's a good one to remember. This one, I remember the summer that this got asked, I think like everyone got it wrong. You can imagine that's a great question to re-ask. Okay. Cool. All right. So that's all we'll talk about for E2. The other reliable elimination reaction is E1. You can do that with alcohols. Primary alcohols, if you dehydrate them, right, they go through an E2 process, usually super, super high temperature, right? So you get something like this. This will turn into water and then, right, eliminate like that. But what's really important are the secondary and tertiary alcohols, because these guys, when they protonate, turn into cations, which react by E1. And E1 will always form the Zaitsev alkene, without a doubt. Okay, so two things to keep in mind there. Alcohols form Zaitsev products, right? And they go through cations, or I guess alcohols go through cations and therefore form Zaitsev products. Okay, so if I had this alcohol here and I were dehydrating it, right, H2SO4 concentrated, right, heat, whatever you want to put here, right? If I wanted to consider the betas, that'd be this guy and this guy. I'm always going on this end here, right? Without a doubt. Okay. I just always recommend draw the cation, because remember, cations can do weird things. They can, jump around. They are, able to rearrange. Because imagine if we had this substrate here, right? And we were to form the cation, right? This cation will for sure shift, because when it does, look what it has access to when it shifts, right? So when I do this alkyl shift here, so it leaves, right? Do an alkyl shift, look at that. Now the alkene that I form, super, super stable, that tetrasub down the middle. Just like that. Okay. Sorry if it's getting a little cramped, and just trying to get through these very quickly. I don't want to spend more than an hour on the review, to be honest. Yeah, cool. So always just draw the cation, and we'll see a problem in today's exam. I believe that if you didn't draw the cation, you would probably get it wrong. Okay, cool. All right, so that's all on the alkene front that we'll talk about. Not much else there. Oh, actually, there's one more example. So one last example is the square. This one's always a tricky one. If you ever do any kind of cationic reaction on this, that forms a cation, right? Forming that cation next door to the ring. So again, we're very familiar with shifts, so totally possible that this could shift, right? But if it is a hydride shift here, we put a cation on the square. Why is that bad? Squares try to be non-planar, like they try to be this kind of V shape, kind of like an envelope shape, because they don't want to have eclipsing bonds. But once you put the cation on it, it's actually forced to be planar, which is very, very bad. You can imagine it's like super, super angry about that, not happy at all. And so not the most stable configuration or conformation. On the other hand, right, we could also just expand and go to 5, and that'll make our life a lot happier, life a lot better, right? So 1, 2, 3, 4, 1, 2, 3, 4. 1 and 4 have had a bond in the past, and we broke it. So 4 breaks its bond with 1 and makes it with 5 here. Okay, so 1 lost a bond, 5 just gained 1, so 1 gets the cation. Okay, but 5 here will gain a bond, and then 5 had this carbon here, so we'll use that as sort of like an anchor point to see where that is. Okay, and so if it's a dehydration, right, we'll just form the cation, or sorry, the alkene as such, right? Just doing the Zaitsev elimination, super simple. Okay. If you have, let's say, as we'll talk about, like an HI or an HX, some kind of nucleophile that can capture this, usually you can get a rearrangement. There's enough time for it, and you'll get capture on that. Okay. The way to kind of circumvent these issues with all these shifts and whatnot is you just put a methyl here. You see a lot of problems where they put the methyl here, and by doing that, that puts the methyl on 1, and that makes it so that it doesn't have to rearrange. Okay, very, very specific example. If you need to stamp something in your brain, it would be this one, right? There's no other way to really write this. It always involves some kind of square with the cation next to it. Okay, cool. All right, but in terms of alkenes, we'll call it there, right? But again, need to know how to make alkenes. We're going to react with them, right? That's our way. So when we get the alkene, right, and we think about its reactions, right? Again, alkene is a source of electrons. So first and foremost, alkenes are nucleophiles. Okay. Alkenes are nucleophiles. That's what it's doing in its reactions. It's attacking, things, and specifically it's attacking electrophiles. So that's why we refer to all the alkene reactions as electrophilic additions, because you're adding electrophiles to the alkene, right? And the alkene's a nucleophile. Okay. And so I'll talk about this really briefly. I didn't want to, but I will just very briefly. But because we're thinking about the pi density of the alkene or how nucleophilic it is, it's really important to understand how EDGs and EWGs work. So how do groups that give electrons work, and how do groups that take electrons away work? Okay. EDGs generally give electrons into the ring. So if you think about like an alkyl chain, they give electrons to the pi bond. So like an R group, or like a pi donator, like a resonator, like oxygen or nitrogen. These guys tend to give electron density, so they speed up reactions, right? So we think about, what increases the rate of a electrophilic addition reaction is going to be an electron donating group. Electron withdrawing groups are things with pi bonds, usually like carbonyls. These guys will withdraw pi density. And if anything, right, so if this is giving electrons, like it's a delta minus here. If I'm withdrawing electrons, right, that puts a delta positive here. So it makes the alkene less electron rich. It slows down the reaction. Okay. So I just wanted to introduce that very quickly, but it's okay if that kind of went through your guys' ears. I just wanted to have said it at least once. But anyways, right, alkenes are typically nucleophiles, and we add electrophiles. So a lot of our reactions is just a question of what is the electrophile that we're adding, right? In a big, in a large amount of reactions, right, that nucleophile is something cationic, or sorry, that electrophile is something cationic. If you can think of a letter to replace with E here, right, probably that letter is H+. So if you think about the best cation in the world, the literal cation, the proton, we can add protons to alkenes, right? And so that can either add to this carbon here or this carbon here, right? In either case, right, one carbon gets the H, the other carbon forms a cation. So do we form both or do we form one? What's going on here? Remember, same with our SN1 mechanics, right? The cation forms where it's the most stable, right? And so generally with acidic condition mechanisms, right, we're always thinking about the most stable cation. Right? So I know that there's this Markovnikov's rule that a lot of people have memorized. I want you to erase it from your brain, okay? I want you guys to always just think about, where is the cation the most stable when it comes to acid type reactions? Okay, it's as long as you know that, right, you can answer any question, even the trick questions that go against Markovnikov's rule. Markovnikov's rule is really bad. It's not a good one. Okay, so think about, where is the cation the most stable? Okay, now if we're in concentrated H2SO4, where there's not much else you can do other than, give a proton, like there's no water or anything that captures this cation, all that can really happen is this reaction reverses. So essentially E1 happens again, right? So we just pick up the proton to stabilize that cation and make an alkene again, right? And so that's even the case with, like, if I had this here and I protonated it, all that can happen is, in the absence of a nucleophile, all we're doing is reversing it, okay? Where things get interesting is if I take this terminal alkene and I form this cation. Remember, this is sort of like what we saw earlier with the alcohol dehydrations, right? We form a cation, but when we re-eliminate, right, we're not re-eliminating the proton we added. We're re-eliminating this proton here to form the more stable product. So concentrated acid for an alkene is really a thermodynamic condition, right? And what I mean by that is that it allows the alkene to slide into its most stable position. So let's say that I had this alkene here and I threw it in H2SO4, concentrated, right? Threw in some heat, right? All that's really going to happen here is we're going to protonate we're going to protonate that pi bond, the alkene, and we're going to re-eliminate, but on that other side, right? And what we get out is this alkene here. Sorry, I apologize. I know my arrows are not very good today. Right, just like that. So consider this a reisomer or an isomerization condition, right? Turning your alkenes into more stable alkenes. Okay, so there's a question again on midterm 4, which it's okay if you guys don't do that one. That was a bit hard, but I'll just quickly write it out. There's a question like this one where there's like an alkene here, and I just throw in concentrated acid, right? When you see concentrated acid and alkene, no nucleophile, think, where is the alkene going to be the most happiest, right? If I think about where that's going to be, not here, not here, not here, not here, not here, not here. It's happiest right here as a tetrasub. So that's all it is, right? So think about where the alkene can snake in. So we'll talk about this in synthesis, but this is like a kind of a trend, right? If I want an alkene to move to a more, if I notice functionality is moving to a more substitute position, I want to, so like, for example, let's say I'm doing a synthesis that looks something like this. right? Where the bromine's kind of moving indoors, like it's moving towards the innards of this molecule, especially towards this more, substituted tertiary. I can consider that possibly an intermediate here is this alkene here, and I can get that alkene via acid isomerization. On the other hand, let's say I wanted to go the other way around. Let's say that I start at the most substituted position and I want to go to the less substituted position, right? Again, that's going to involve me using alkenes that are less sub, right? Because I can imagine that possibly an alkene intermediate is this one here. So I call this kinetic walking. The way this will work is you'll have to use, who makes the less sub alkenes, right? Those are the Hoffman bases, right? The terpetoxide. So we'll see a sequence where you can do, what we'll see is HBr ROR with a bulky base, and we will be getting out these less sub bases or less sub alkenes that we can use to sneak outside of the molecule. I call it kinetic walking. Cool. All right. Anyways, isomerization, right? If you have concentrated acid. If you have any sort of nucleophile though in that acid, then again, the cation obviously can get captured by the nucleophile. So let's say I have HNu, right? I go through a cationic intermediate, and then the Nu can just attack. Super simple. Right. And the nucleophile can be a lot of things, right? It can be water, it can be alcohol, it can be thiols, really anything. It can be halides too, right? These are usually the typical culprits that we see because these are our nucleophilic acids, right? H3O plus, right? For either one of these cases, or all of these cases here, right? H3O plus is what you usually see, or H2SO4 or something like that. For this one, it's just literally halide acid, HX, right? Again, one thing to just keep in mind is that let's say that I have an alkene such as this one. Let's say I'm doing this in HBr. Right, we'll protonate on the cation. Protonate on the alkene to form a cation, and then this can shift. So always in these acid mechanisms, please just draw the cation, right? Just draw it, because you never know what might happen, right? Remember that you can also do alkyl shifts too, right? It doesn't have to always be hydride shifts like I've been showing. Right, you can do alkyl shifts too. Oops, sorry. So we can get attack on either one of these. Right. So always draw that cation, folks, and that way you can see if there's a shift or not. Just draw it on the side, right? Cool. So an acid nucleophiles can capture, pretty simple, not too crazy, right? And then again, that one example we went over where, if I have something like this, and I form that cation next to that square, obviously the square is going to open up, okay? Now, we'll talk about this a little more when we get into like actual stereospecific reactions, but, we can talk about how the H and the Br will add, or like the H and the X will, or the H and nucleophile will add, relative to each other, whether they add syn or anti. So if I have a pi bond, like this one here, sorry, this one here, and let's say I do like a DX reaction. So D is just heavier hydrogen, right? Right. D will add here, and then X will add here, right? Because the cation that forms is this one. So the X will add here. Okay. What is the relative stereochemistry of D and X? Are they both going to be the same? So are these both going to be wedges? Are they going to be one wedge, one dash, right? What's it going to be? Are they syn or anti? When it comes to the HX reactions, it really doesn't matter. For most of them, they are usually a mixture of syn and anti. So you'll form this is the anti product because D and X are opposite to each other. The syn product will look like this. Right. You'll form both, and you'll form both isomers of this. So you'll form I didn't know that D was as a dash here or as a wedge, right? I didn't know that. I just guessed, and I'd put plus and minus to cover for both. I guess racemic would be the other term you guys are looking for, right? But either one of these could form. So technically this reaction has 4 products. Okay. So usually in questions like this, where it's not stereospecific, we will call this stereoselective really. When it's not stereospecific, usually they'll make sure, professors will make sure that the question is written such that you don't form an anti or syn, you only form like one chiral center. So for example, if I did HX, right? Now this is H, and who cares, right? H doesn't have chirality, and actually this doesn't have chirality either. So maybe I throw in this just to make a chiral, right? But you'll just form one product here. These are the same. So that's usually what'll happen. But there is some stereoselectivity or stereospecificity when you do a reaction with a tetrasub alkene. Okay. And so that works like this, right? So why does this give us stereoselectivity? So when we add on the proton, okay, it might even be easier to look at it from the 3D perspective, right? But when we add the proton on, we're going to have a CH3 and an H on one side, right? That are kind of, hanging out. And then we have this flat methyl with the cation, okay? When the nucleophile, let's say X in this case, comes to, interact with the cation, right? Because again, there's two lobes here going to attack. Attacking from the top is going to be pretty hard because, CH3 drawn doesn't look too bad, but if I draw it, it really looks like this, right? It's a CH3. It's like a helicopter blade. It's constantly circling. So if you imagine, right, the X minus can be intimidated to walk through the helicopter blade, to get to that orbital. It's easier to just come from the H face, right? H's side is a lot more clear. And so what ends up happening is we end up forming a syn product. Okay. But again, don't take this as syn is always the answer, right? Syn is only the answer with tetras, right? And for good reason, right? There's a steric effect. So we'll talk a lot about steric effects as well with these reactions. Steric effects are pretty big. You can imagine that there's something big and bulky on a molecule, right? That's a key to you that, hey, maybe I want to react on the other side of that, right? So we'll see that especially with alkene reactions of cyclopentenes, right? A reaction like this, almost always whatever's adding is going to be opposite. Almost always, like 99% of the time. Okay, cool. All right. But that's the HX reaction. And so again, if we go back to that substrate that I talked about, like this one here, where the cation forms, right? And then it kind of just rearranges. It's kind of an issue in synthesis, right? Because if I'm a chemist and I form this alkene here, I want to inspire vicinal difunctionality at that position. I don't want it to rearrange, right? That's kind of a nuisance to me. So what do I do to solve this problem, right? Well, think about it. Right? The issue is that when I add H+, I form a carbocation, and it's carbocations that rearrange. So what if we formed a cation, but it wasn't on the carbon, right? What if we stored the cation in some atom? Right. This is the introduction of the triangle mechanisms, which all kind of involve something like this, right? Attacking some A group with a leaving group, right? In this sort of fashion. If I want to draw this even better, right? Draw something like this, the leaving group leaving like that, the triangle. And so what I get out is this triangle here. Okay. This triangle is our solution because no longer do we have a carbocation that rearranges, but we have a triangle cation. We have an atom with a cation in it, usually some metal, that can store the cation and make sure it doesn't rearrange. Now, it still inspires reactivity, right? In this case, we still have a higher cation on that more sub position, just like an epoxide. You guys might remember epoxides and acid do this, right? The more sub side is attacked usually. Same exact kinetics here. But now if I have some nucleophile, right, it's going to attack on that more sub position of the alkene, right? So that position that would stabilize the cation the best, but without that nuisance of rearrangement. Okay. And so this here is usually the final answer for what we see. Okay, cool. Usually the first one we'll talk about in this class is the mercuric acetate ion. So what it looks like is this written down. You guys' mechanism for this is pretty weird. If you follow my arrows, you'll be fine too. But usually you'll have Hg, and then there'll be like an OAC here, right? Again, attack, be attacked, kick off. And what we get is the mercuric cation. And then, usually in these reactions, you have some kind of oxygen nucleophile. So we have this water molecule here. Water can go ahead and do the opening. Okay. It'll do on the more sub. And what we get, right? I'll write then NaBH4, and I'll write why I'm writing that. But we'll get Hg here, and we'll get OH here, right? Again, depending on the stereochemistry of the ring, which we don't know what it's going to be, it can be either wedge or dash, right? But we'll get to this point here with the water. Something will depronate the water into OH, and then NaBH4 will reduce the Hg into H. Okay, so we know that. We know to write it, okay? And that's how we do this mechanism here. So we form a triangle, and then we crack it open. Right? We crack it open that same step. If we use an alcohol instead, right? Then this is just OR. Nothing too crazy there. Just what it is. What this reaction really introduces to us, and it makes this material, tad bit harder, but once you see it once, you remember it, is imagine if I had this substrate here where I had an alkene with this alcohol tail or alcohol arm, right? When I form that mercurium ion here, let's even say that there was water in this. So we'll say He+, say there was water in this, right? A lot of people are inclined to go ahead and just open this up with water and say, okay, water opens on the Moore sub, and then He is reduced, right, into H. Well, guess what? This is actually not the answer, right? The actual answer is going to be that this guy cracks it open, right? The intramolecular arm. And so this here, when an alkene is tethered to some nucleophile or some atom with a lone pair, is the absolute key to intramolecular reactions. Absolutely the key, right? If you see this, you know that's exactly what you're being asked to do, or at least being asked to assess the ability of. Okay, so keep that in mind, right? This isn't drawn here for no reason. It's there for a function. A lot of people always wonder, why is it that that's faster? Because, it's like, oh, water is so much, there's so much of it. Shouldn't it be faster? Well, here's the thing, right? As you're forming the mercurium triangle, so, as you're going through a transition state, the molecule starts to curl up, right? Because alcohols are delta minus, and this is positive. So you already have this curling up motion, and the alcohol is already tethered to the molecule. So it just has a higher chance, above random chance, to, be aligned with the orbital that cracks that open. Sorry, this would be opening on this side. My bad. So yeah, so look out for these nucleophilic arms, right? The way that I draw these or number these so that I always get these right, the atom attacking, so alcohol in this case is 1, atom attacks is 2, and then everything in between, so 3, 4, and 5. So that tells me that this is a cyclic ether, right, with oxygen in it. 1, 2, 3, 4, 5. Carbon 2 has this carbon here that's sticking out. It's going to have the Hg on it before reduction. If there's anything on 3, 4, and 5, you can add it in. So if there's an ethyl on 5, add it in. If there is an isopropyl on 3, add it in. Right? So cool. That's just how I do it. So you're welcome to use my method. Again, Hg gets reduced off by the by the NaBH4 in that second step. Okay, cool. So not the answer. It's actually going to be this here. Okay, cool. In terms of stereoselectivity, just like with HX, this reaction is not usually stereospecific. There's no anti-syn here. So when this question is usually asked, it makes, usually make sure that there's only one stereocenter. So in this case, one stereocenter. So this would be racemic. And even this one here, right, where we did earlier, this has one stereocenter, so racemic. If it's tetrasub, it's going to be both anti-syn, so it's best to avoid that. Okay. So usually you'll have something like this, right, as opposed to anything else. Now, it's not that, I guess earlier I said kind of that, this is the introduction to it. You can do intramoleculars with acid mechanisms. I guess the coolest example of that would be this here. Yeah, this is probably the coolest example. Wait, hold up. Now it would be. So if you want to try this, you can pause and try this on your own. But this would protonate on this here, which would rearrange almost instantly into this, and then this would capture on that, right? So that would make a 1, 2, 3, 4, 5, something like that, right? So that's a cool one. Again, that nucleophilic arm really just kind of gives away to you what you need to do there. It's like super, super, super choreographed is what I say. If I did a mercuric reaction here, that would just give me the attack on this side, right? Because this would turn into the triangle. 1, 2, 3, 4, 5, 6. So I'd get a 6-membered ring here. So look at that. I kind of inspire different selectivity depending on what I attack. It's kind of cool. I think you'll get something like this. Might be wrong. I don't really care, to be honest. Cool. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Yeah, I think I'm right. Cool. All right. So mercuric acetate brings up the first triangle. Are there any other triangles I can make? Of course you can. Right? The one of the most famous triangles is the BR2 triangle, or the X2 triangle. So we'll just use BR2 as an example here. But if I react BR2 and tetrachloromethane with this alkene, what I'll form is a BR triangle, right? So again, same idea, right? Attack, be attacked, and lose some leaving group. Wow, BR is a leaving group. Who would have guessed, right? I'll form this triangle here, and then something in solution can crack this open, right? Again, on that more subposition. So I get this here. So I get a dibromination. So this is actually the first reaction you guys learned where you actually take advantage of the vicinal functionality or difunctionality. You actually difunctionalize the alkene, right? I mean, as of right now, we've just been adding H in something, and H isn't exactly functionalizing. Okay, but we can go ahead and form the Dibromous species shown here. Okay. Cool thing about this reaction is, let's say I did this reaction on an alkene that has two positions like this or something like this. The triangle that forms, right? Let's say it forms as a wedge, right? Is always going to be cracked open on the opposite side. So if it, let's say, attacks here, or I put the methyl here, so it'll attack on the more subside, right? When it cracks this open, right, the BR are going to be anti to each other. Okay, I know this isn't chiral, it's just to exemplify a point, right? They are anti to each other. So our very first case of actual stereospecificity where it matters, and also the first reaction where you will definitely be asked a question where you form two stereocenters, right? So usually, typically, you'll use some kind of ring, and then you'll see like BR2 and like, you know, CCl4. You can actually even generalize the nucleophile. If you use a nucleophilic solvent like water or like alcohol, anything that's like anything below the arrow that's also a nucleophile, that will also react here. Let's say that I form again the wedge bromide here. Sorry, I don't know why I drew that bond there. Right. Water in this case will crack open on that more sub side, which is going to come from behind. So water will, add as a dash, pushing that methyl to the front as a wedge. And then the BR here will be a wedge. Okay. And so this selectivity, that's one thing we test on. The other thing is the nucleophile generality, right? Which is that the solvent, if it's nucleophilic, will just crack open. It's going to go ahead and crack open that carbon or the triangle before the other bromide does. Okay. Now, why does it beat out the other bromide? It's because when you have a solvent, you have millions of these molecules per one molecule Br2. So you can imagine the other Br minus is getting slowed down heavily by those other millions of water molecules, right? There's so many more of them, right? So either one of those can attack, to be honest, and there's more of the water. So it wins out in the concentration battle. Okay, cool. So knowing that Br2 is anti, and then that nucleophilic solvents can crack open on that more subside, very, very important. Okay. And again, let's say I had a nucleophilic arm. Whoa, right? If I did Br2 here, guess what? I'll get a ring. So this will attack here. 1, 2, 3, 4, 5. I'm really liking the 5-membered rings. I'll draw the bromonium that would result. Okay. Crack that open. Right, 1, 2, 3, 4, 5. 2 is going to have a methyl on it. That's always going to be the case in these cyclizing questions. If you're cracking open on that closer side, we'll have a bromine on that side like that. And so again, we can see that vicinal difunctionality, right? An easy way, if you ever get a ring, right? So let's say you were to get a ring on the exam for synthesis or whatnot. We'll talk about this again too. And you get that vicinal difunctionality. You just got to cut across that vicinality. Draw everything without those bonds, and you have the two things that add across your pi bond. You have an OH and a BR, right? Or in this case, BR2, really, right? So easy way to kind of figure out what to do if something looks really weird, right? Let that vicinal difunctionality guide you. And again, we'll talk about that again too when we talk about synthesis. Okay, cool. So this is totally possible. Okay, a lot of things can add vicinally, right? Just got to look out for that. Okay, let's say that I had this and I had Br2 and NaCN. Right, that's just gonna, I mean, you can draw it out. Br will form like that. I guess actually we'll do this. Yeah, let's just do this. Just so we form two centers there. We'll form the Br ring like this, and then CN will crack open on that side there. So look at a Br here. Let's make this Br a wedge, and then we'll make CN here a dash. Right, it doesn't matter what you make the other one here, wedge and dash. Just do that. Okay. Now, again, I didn't do a very good job of this. So again, to make this clear, All you know is that this is going to be anti. You don't know the specifics of it. You don't know if it's specifically wedge dash or dash wedge, whatever. So always remember to write racemic or something, or to draw the other isomer, right? So I'll draw the same thing, but I'll draw now Br as a dash. Just keep that in mind. Oops, sorry. CN will be here now. There we go. Okay, cool. So it's anti-addition, just like that. All right. So the X2 reaction kind of just teaches us that we can have, you know, an XY combined with each other, and that can form to make a ring. Where these questions can get a little interesting is when we have two different halides connected, like I and Cl. And the question becomes, right, how do these guys add across? Well, I and Cl is more electronegative, so there's an internal dipole like this. I is the more electrophilic atom in that bond. So the less electronegative atom tends to form the ring, and then the more electronegative atom tends to attack on that more side, right, to open up that ring. Okay. Cool. All right. So those are the X2 reactions. That's all I'm going to really talk about on those. And again, we'll see them anyways in these problems. So nothing to worry about there. Again, this could be dash or wedge. So we'll include that like that. Cool. Are there any other triangles we can make? Yeah, of course. There's a triangle we can make that we've known our whole lives, right? We can make the epoxy triangle. Okay. So epoxy triangle uses MCPBA. Again, this reagent looks crazy, but it's not that crazy once you realize, oh, it's the same thing, right? We just attack an atom attacks back, and then we lose something. In this case, we'll just lose this group here. You'll see these extra arrows here. They're just kind of fluff. Don't worry about them. I'll just memorize them. This bond goes here, and this bond attacks H. It just it makes it very clean, and you don't have to do any deprotonations afterwards. But one important thing in this class is that you need to draw all byproducts that are organic. The MCPBA byproduct is always going to be this. Well, MCPBA is going to be a little difficult. MCPBA looks like this. So this is the byproduct always of MCPBA reactions. If it's the other one, CF3COOH, then the byproduct is CF3COH. Okay, so this carboxylic acid is the byproduct of this reaction. Okay, cool. So we can form epoxides, and remember epoxides, we have ways of cracking them open. We can crack them open in acids, so H3O plus, and or let's just do like ROH, H3O plus, right? That would open up on the more subside, so OR adds here, OH adds here. All right, if I want to reverse that selectivity, open up on the less sub, I use base. So now OR will be here, OH will be here. Okay. You might remember if you watched the video I made last quarter on synthesis, when it comes to vicinal difunctionalities, epoxides tell is that there's some kind of alcohol or some kind of alcohol derivative, right? Let's say I took these guys and I did chromic acid, so like Jones. You can see how quickly the complexity is raised in these problems, right? But these guys are just, I mean, they're oxidized alcohols. So you can always trace back oxidized out like carbonyls to alcohols, and then alcohol vicinal to some nucleophile is always a trace back to the epoxide. The OH in these cases is always the epoxide OH, or is the epoxide O, sorry. So that always tells you that the other thing, right? The OH is the epoxide. The other thing was the nucleophile that cracked it open, right? That can then give you intimate detail as to whether you use base or acid, right, to crack that epoxide open. Okay, cool. But epoxides, hey, can crack this open. Pretty cool, right? And now we know how to make them from alkenes. You can definitely expect predictive products with epoxides, and also to use them in synthesis. Very, very useful. Okay, cool. Anything else I want to talk about that? I don't think so. So we'll just keep it chugging along. Oh, I guess one thing we could talk about is I guess if you had this, needed MCPBA, right? You could form this here and then do acid or base 1, 2, 3, 4, 5, right? 6. So whether you attack here or here will depend on whether you use acid or base, right? So H plus probably this way and base probably this way, right? Cool. All right. Oh, one last thing. So one last thing with the epoxide. So because of this byproduct, the acid byproducts, it's an acid, carboxylic acid. Realistically or practically, sometimes it's not the best solution. Sometimes people just don't like using it. So there's actually another way of doing this, and it uses the X2 reaction. Okay. So remember, we're going to form the bromonium here. And then water opens up on the more subside. So water will be here. Again, it'll be OH2+, but something will be protonated in solution, right? Again, we're thinking transformation is not necessarily the mechanism here right now. But if I add an NaOH, right, or NaH, either one of these guys are going to deproton the alcohol, and the alcohol is going to go ahead and hit that bromine center to form an epoxide. So this is an alternative method to forming epoxides. And it kind of relies on the triangle mechanism a little bit. So whether this is a wedge or a dash here will depend on, you know, which one you form. The coolest problems I've ever seen with these is whenever you have a little bit of sterics involved. So let's say I have this here. You can try this on your own first. I would highly recommend it. But what would happen if I did this reaction, right? How would it look? So I did this into NaH. What would the resulting epoxide look like? So that methyl there, right? We can imagine, say, sort of helicopter blade. Br2 doesn't want to encounter from that side. So Br2 will form this here, this bromonium here. And either one of these sides are completely identical. So it doesn't matter which one water opens. What's important is that when water does open this, right, it is opposite. It's always opposite, right? So we always form this here. Now, when we deprotonate this and we click, we click onto that carbon there, guess what? We form the paradoxical product, right? This doesn't make any sense at all, right? Because it's like, how in the world do I form this epoxide here that's the same pace as the methyl? It's because we first took advantage of the bromine forming on the underface, and then, had the alcohol add on the upper face. It was forced to, it had to, and then close in on like that. Okay, cool. So how can I get it to just react on the other side as normal, right? This would be fairly easy, right? What reagent can I use, right, that maybe forms a triangle that would just add the epoxide on the other face, right? So instantly in one step, we'll just add this way because it doesn't want to approach from the methyl side, MCPVA. Sweet, right? So we get this cool control on stereochemistry using sterics, right? So very cool problem. I should have wrote this one honestly on that exam, but I don't know why I didn't. I think it's pretty cool though. Cool. All right. So that's all we'll talk about the epoxide. All right. Any last triangles? I think the last triangle is the carbine, which has a couple different ways of being formed. You can form it with CH2N2, so diazomethane. Carbines are interesting, but we'll first talk about this one. This one, CH2N2, right? N2 is the world's best leaving group in the world, and you'll learn about this more in the rest and at the end parts of this class. But N2 is always itching to leave. So doing the attack on on the C and whatnot, it's very, very simple and easy. We'll lose N2, but we'll form a triangle here, a literal triangle that we really can't do anything with. So if you ever see this in synthesis, the triangle tells you there is an alkene there. It also tells you that was probably their last reaction because there's nothing else more you guys can do with this. But it's a very cool reaction. Another thing that does this is CH2I2 and zinc copper. This is what we call a carbinoid. Exactly what exactly happens here is CH2 forms this sort of zinc iodide bond where zinc to CH2 forms this minus here, and zinc to iodide forms this sort of positive here. And a carbene in of itself is just that. It's a carbon that is anionically and cationically charged. This will make more sense when we think about the more common method of making carbines, which is the chloroform method. Okay, so I have this here and I have an alkene. How does this work? So terbutoxide is a strong base, and chloroform's proton is actually very acidic. This proton's about 16, which is about the pKa of the alkoxide. So it's really easy to pull this off. And when you do, right, you form the species here. And for magical reasons they don't really need to understand, this chlorine can depart. Okay, what it does, it forms this cationic anionic carbon species that we call a carbene. Okay, a carbene, if I kind of draw it out, the whole chemical structure would have two groups on it and then a lone pair. So it's a sextet. right? It is a sextet molecule, only 6 electrons, but it isn't necessarily nucleophilic or necessarily electrophilic. It's a little bit of both. So when we have an alkene, the carbene, actually, let me just draw this up here, right? When we have an alkene, the carbene can essentially, if there's a positive and a minus, it can attack and it can be attacked, and it will form the triangle. So that's what a carbene is. So that's why this carbenoid with this is called the Simmons-Smith, right? That's where this comes from. This anionic and cationic interaction, right? Or that's what we need, right? And that's why it works. Okay. Again, this is sort of an end game kind of thing. So in synthesis, if you see it, you know exactly where it came from. It's not much more else than that. Just keep in mind that the chloroform method gives you the diCl. Okay, gives you the diCl. Now, for those of you that want a little extra challenge, here's a really cool problem. So I'll tell you what, you can write this down. And if you need an extra hint, I can give you the answer and you can work your way through this. But the mechanism of this one is a pretty cool one. So, I mean, obviously we know what this is going to do, so I'll just get rid of that part. But the reaction of this carbene with this pyrrole is really, really an interesting reaction. So consider it if you want the extra challenge. Cool. All right. I think for triangles, though, that should be good. I think we're done pretty much. Not much else on the triangles. So yeah, cool. Again, I am going through this very quickly, so I apologize. Remember, the point of this was to just review. And I think we're about to hit the hour mark, or we already have. So I kind of have to speed this up a little bit. But anyways, yeah, we're just trying to get you guys familiar with reactions so that if you see them on the exam and you had to guess, you can at least guess somewhat the right answer. Cool. So the next section of reactions is going to be the triangles, or sorry, not the triangles, the Trojan horses. And so what are these reactions? So you'll notice with a lot of these reactions, we tend to have addition of the nucleophile on the more sub. So for example, like mercuration, HX addition, Br2, where the nucleophile adds more sub, right? We tend to see that, right? Like this is what we tend to see usually. The Trojan horses, what they do is they say, okay, they pose the question of if I can get the more sub, how do I get the less sub? Okay. So how do I get this alcohol here and possibly this bromide here? The answer is you got to trick the molecule. Okay. And so that's why I call these the Trojan horses. You give them an electrophilic gift that we transform into the atom that we want, right? And so the first one we'll talk about is the boration reaction, just very quickly. Again, we'll talk about mechanisms later. But the boration reaction, if you see this, you're just adding an OH on that less sub position. What makes this reaction very interesting is the borane, because the borane kind of is directed to this position, right? Like I mentioned, the borane, we're going to deliver the borane to the molecule, right? And then we're going to turn it into the alcohol. Okay. So why is it that the borane wants to go less up? Two reasons, right? First reason is that if I look at borane, right, periodic table, right? Periodic table kind of explains both trends. Okay. One trend is that in terms of atomic size, right, atomic size increases this way. So if this is a carbon atom, this is a borane atom, right? Borane is significantly larger than a carbon. Maybe not that much. This is much of a dramatization, but it's larger. So if there's anything, if a carbon feels a steric effect, borane feels it times 100. And so anything that's sterically inhibiting or hindering, it's never going to attack there. So, sterically, borane wants to go here, right? Borane wants to go there, right? Just because of hindrance. Okay, so that's like the biggest reason, hindrance. Okay, literally bigger reason, right? The other reason is if I look at borane, right, it has, it's in this column before carbon. It has 3 valence electrons. So at any point in time, borane only ever has 3 bonds, right? It only has 6 electrons. It is a perpetual sextet, right? To put that into perspective, that means that it's essentially a carbocation. It is always electrophilic. In fact, borane in solution, you can't buy BH3. You have to buy BH3THF or BH3 or B2H6. And B2H6 is this here. Okay, it's essentially borane connecting to make these sort of half bonds, right? To stabilize itself. You can also use the THF version, just has a THF molecule, which looks like this. It just donates the electron pair into the borane to stabilize it. So borane has to be stabilized if you buy it. That's how electrophilic it is. Okay, so electronically, borane is always electrophilic. And again, if the trend of these reactions is that the nucleophile adds to the more subposition, right? That means that our electrophile has been adding to the less subposition. We just haven't said it out loud, right? I should have been saying it out loud, that the electrophile has been adding here. So in order to trick the molecule into accepting oxygen or bromine into that less subposition is also to say, how do I make an electrophilic oxygen or an electrophilic bromine? On the oxygen front, it's pretty difficult to do that. It's really hard to make an O+. Not impossible, but hard to make it. But borane offers a solution because we can essentially in the mechanism transform the borane into an OH. Okay. Which we'll talk about the mechanism later. Okay. So that's the beauty of this reaction is that you're essentially tricking the molecule into accepting borane and turning it into oxygen, sorry. The other thing about this reaction is that borane and hydrogen complex on one side of the pi bond to add on, which means that every single time you do this reaction, you're always adding the syn. So this is our first syn reaction, right? We've seen an anti-reaction. Now we're seeing a syn reaction, okay? Triangles are anti, right? Borane is syn. It's a good way to remember it, okay? And this is what we see, okay? So that would mean that, I mean, in the case, obviously this is not chiral, but I guess I could possibly make it chiral, right? That work out? Yeah, I think this would work, right? You would have to indicate, I would go out of my way to indicate that that H is syn to the OH when it adds on. Okay, cool. So all we're really going to talk about there. I mean, the only other thing we could talk about here is this right here, which would give us the alcohol like that, but who cares about that, right? This is not chiral at all, but this would give you the BH3-THF reaction. Or sorry, BH3-THH will give you this product. So I wouldn't say sorry. Okay, cool. All right. So we'll move on from there. Ran out of slides, so we got to go back to the beginning. Anyways, the only other Trojan horse we have is the HBr ROR reaction, and this one is not too crazy, right? If you see ROR HV, that just means the borane, or sorry, the bromine adds to the less subposition, or that electrophilic position, right? Nothing too crazy. In terms of stereoselectivity, there is none, so it's not anti or syn. So, right, this will be plus minus. Right. Common trick question is, what if I did this reaction with a chlorine? Guess what? Nothing's different. Chlorine just adds like, chlorine just adds like that. The reason for this is just math, right? Chlorine just doesn't have the right radical math to do it. Bromine does though. Another atom that can do this though is sulfur. So sulfur and bromine are the two you need to know. They're the generalizable ones that can do the the electrophilic addition where it goes on the less sub. Chlorine and iodine can't do it. Okay. That's usually about it for these. It's nothing too crazy off of that. Cool. All right. So with that being said, all we have left on the alkene reactions are the crowns. And I call them the crowns because if we look at them, they go through this sort of okay, yeah. So it's because they kind of go through this, something like this where A can be like a metal or it can be an oxygen, right? Ozonolysis would have this as an oxygen, right? So maybe we can look at that first. So ozonolysis, I mean, as a predictive product is super simple. So let's just do that for now. We'll talk about mechanism when we get to it. Predictive products is super simple, right? You're just literally cutting down the middle here. And you're just putting oxygens where you cut, right? So usually the problems with these are just complex alkenes, something like that, where you just kind of O3 across that. Not too bad, right? Now you could control this to one alkene. It's a bit difficult though, and usually, oh sorry, not that. But usually you'll just see this reaction done in high excess. So you see like excess O3, so that everything cuts. Not very usually do you see it reacting like with one of them, like on an exam. Usually you just want to cut all of them. Okay, cool. So O3 is really not that bad. And again, mechanistically, we'll talk about when we get to mechanisms. The only other one is the OSO4 reaction, which when we do this reaction here, I think this one's also followed up by some kind of reducing agent. Yeah, it is. You'll form this here. It's an OS now instead of a oxygen, and then this just decomposes into the diol, but particularly into the syn diol. So this is our second syn reaction. It's our only other syn reaction. Okay, cool. So we get a syn diol. The sort of complement to this reaction is if you did MCPBA into a hydrolysis, remember the triangles are always attacked on the other side. So if I did a hydrolysis after this, whether it's in base or acid, doesn't matter, right? What you'll get is an anti-diol. Okay, so that's usually the difference between those two. Cool. But with that being said, we've now in the last hour pretty much sped run all the alkene reactions. So that's great. Finally, thankful to get through that. I mean, it's a lot of reactions, right? But hopefully there is, some pattern you guys can find. Alkyne reactions are pretty much the same. You're just kind of doing a lot of double additions to them. So for example, if I do HX to this, usually, right, you're doing an excess of this so that you just do a double addition. One equivalent can usually stop at this position here, usually, right? Like you can get away with that. So like, let's say it's one equivalent, right? But you'll usually see this done in excess. And so that will just have a double addition. So now when you have a geminal difunctionality, that gives rise to it like an alkyne. That's kind of triggering that you want to use an alkyne there. That's the signaling element, right? If I were to do an X2 type reaction, so CCl4, right? Again, one equivalent would give you the vicinal dihalide, vinyl dihalide, but you're usually doing this in excess. Gives you the tetrahalide. Okay. So a lot of functionality can get, can tell you, oh, I'm doing a alkyne type reaction. Okay. Where alkynes get a little interesting is in their hydration reactions, because if I were to hydrate them, so usually you'll see this done in a mercury solution. Okay. Again, as to the more subposition, this is known as an enol, and enols very, very quickly do something we call tautomerize into carbonyls or their keto form. So visually what's happening is the pi bond sort of moves to where the oxygen is to form that. Okay, so we can actually form ketones from alkynes. If you wanted to, you could use R2BH, THF, and that would form the other enol that would lead to the aldehyde. Okay, just like that. So remember, this is a big thing people always mess up. People associate keto enol tautomerization. So this here is a tautomerization. People associate this with only the hydration reactions, like these specific ones. Anytime you make an enol, it is game for this reaction. Anytime, absolutely anytime. So if on the exam you were given like an ether hydrolysis, I know this is an old reaction, but you could still be given it. You're given an ether hydrolysis where you're doing HX and you form, right, this alcohol with this iodide or this halide. This is an enol that's going to tautomerize, right? That's going to turn into this aldehyde here, right? That's just the way it is, right? If there's any other reaction that can add water, right? For example, let's say I have an alkyne, I do X2 or Br2 and H2O, right? This is going to add, remember, water in the more sub, Br on the less sub, right? Hey, guess what? That's an enol, despite not, initially appearing as one. And so we get the alpha bromo ketone. Okay. So totally, just look out for that if you see it mechanistically. Okay. Cool. So hydration reactions are a bit wild in that sense, but it's still there. We can do the same Trojan horses. I mean, we saw one of them, right? We saw this one still works. The HBr reaction also still works. ROR. right? That'll give you the bromide on the left sub position. Usually this is limited to one equivalent, because if you do two equivalents, you actually get the vicinal bromide, which obviously doesn't initially make a lot of sense. So it kind of, hurts your brain a little bit. But that's just, just to be aware of, that would be what would happen there. Cool. So what else can I do with alkynes, right? Other than HX, hydrations, X2s, and HBRs. A lot of the old reactions don't really do, like you don't do ozonolysis, you don't do carbines. Oh, I realized I forgot a reaction for the alkenes. So we'll talk about these together. So one reaction I forgot with the alkenes is you can also just hydrogenate across an alkene. So let's say I have an alkene here and I do an H2PD reaction. This is just adding H2. So it just turns this to an alkane. Okay. Now, the significance of this reaction is that if I were to have a tetrasub and I were to do H2, right? This reaction, I erroneously said that there was only 2 syn reactions. I lied. There's actually 3. This is also a syn reaction because H2 will add on the same side. Okay. So we'll get the same side addition as such. Okay. So this is also a syn addition. The reason for this is because on the metal, right, the alkene has to fly into it, right? So when this adds on, it's always going to add on syn, right? Because it's adding on the same side, right? It's going to complexate on the same side. Okay. Where this gets interesting is when you have, again, local sterics. So let's say that I have, again, I mean, the traditional example in this class is the triangle, right? That offers so much sterics, right? When I do hydrogenation on this, right, it's always on the opposite face here. Yeah. Don't be afraid of D2. D2 just means it's heavier hydrogen, so they just want you to track where the deuteriums are going, so that they can see that you understand what's going on, right? We can see here clearly that they're going to add to the opposite face. Okay, so we can hydrogenate alkenes, H2 and some like platinum or PD, don't matter. Sometimes you see over carbon, no big deal. Okay, alkynes are the same way because they're also just pi bonds, right? They can also just hydrogenate. Okay. So we can do H2PD, but again, alkenes also react. So alkynes will turn into alkanes if you just hydrogenate them as such. Okay. But we can stop this. We can use something called Lindlar's catalyst. Okay. That will stop this to the alkene. And again, just like before, it is a syn addition. So it is always going to add syn. So if I had an alkyne that's not terminal, like I've been using for the most part today, like this one here, H2 Lindlar's catalyst, we'll get a cis alkene out of this. Okay. If I want the trans alkene, so let's say that I want this alkene here, we use a metal reduction known as Birch reduction and a solid ammonia liquid, and that will give us this alkyne here. Okay, cool. All right. So we actually, from alkynes, have access to alkene reactions. Cool. All right. So the last alkyne thing we need to know that I can think of, let me just actually sneak peek real quick at the review doc for this. Sorry, I'm realizing this is taking way longer than I thought. I thought I finished in an hour. We're going over an hour now, so this is a little, I apologize. I think mechanisms I probably won't have time to talk about in this video, so I again apologize. It's because I have to get through the midterm too. But yeah, all that's left now is the alkyne anion, which you can use the terminal alkyne for. So terminal alkynes are relatively acidic, which means that if I have like NaNH2, which reminds me, I have to go over the synthesis of this too, goddamn. A lot of material, right? Anyways, we can form the alkyne anion. And so the alkyne anion, you can attack primary halides with to form new CC bond. So it's like a type of Grignard, right? I mean, it is a Grignard, it's a carbon anion, right? So it's a type of Grignard. You can attack carbonyls like ketones, which will give you a direct connection to an alcohol with R groups of your choice. You can also attack epoxides, okay? And so epoxides, the usefulness here is that when you crack these guys open, right, the alcohol is like a little farther down. It's like 2 carbons down instead of just being, right there. Or I guess another carbon down is what I should say. Okay, cool. So that is the alkyne anion. And then, from here, you can choose to Like let's say you can do like an H2PD or like you can do whatever you want with the alkyne, right? Once you've transformed the carbon chain. So if you ever think of doing some kind of Grignard reaction or something, try to consider using alkyne. That's usually, it's a lot better than using the alkene or the alkane. Okay, cool. All right. So finally, we're almost at the end. We have one more thing I want to talk about, which is just the synthesis of alkynes. Easiest way to do it is do a dibromination. And then you do a double elimination. So you'll do one elimination this way. And then you'll do this elimination. Okay. Why does this occur? Why is this allowed? Because these hydrogens next to bromide are the most acidic because of the bromides. And yeah, that's pretty much like the driving force of this. Okay. Now, one thing that people always mess up every quarter is why do I need 3 equivalents of Na and H2 for why do I need 3 equivalents for terminal alkyne synthesis? Because after you go through one round of this in this reaction, you have this bromide here, this dibromide here, you have this hydrogen. When NaNH2 has to make a choice as to who it deprotonates, it is never making this choice here on the sp3 carbon. sp carbons are way more acidic, and so you're going to quench your NH2 minus on the alkyne. So if you don't do 3 equivalents, you're going to end up with a mixture. So the solution is throw in a third equivalent to forcibly deprotonate the alkyne. And then now this alkyne will not go and hunt other protons, or it won't hunt NH2s, right? And quench them. Okay. So that's the problem you're solving with this reaction. Okay. So you need 3 equivalents for the terminal, but if it's internal, you only need 2. So something like this, right? You only need 2 equivalents. You can, for the most part, shove all this onto an arrow, and you're usually just good. Just turns the double bond and triple bond. Okay, cool. All right. With that, we've got to call it on the review of the material. I apologize. I know I kind of sped through it. I kind of had to, right? If I didn't, I'd be here for another hour, right? Explain this stuff. But cool. All right. So hopefully for those of you that are completely lost, that helps you out a little bit, at least on the reaction front of things. Highly recommend, actually. It's a good time to take a break if you need one. I might need one, but I won't. It's whatever. Let's just get into the midterm, just because we got to get into it. Okay, cool. So again, all that review was to help you through the predicted products mostly and somewhat of the synthesis. Unfortunately, today we definitely won't have time to go through mechanisms and what to think about them. So I apologize. Maybe I'll do it in another video. But for the most part, use your notes, use the review doc. I put a lot of time and effort into those for the sole purpose of making them easier to remember. Cool. So we'll get into this. Multiple choice. These are always gonna be concepts in the class that you went over. So I'll just kind of quickly highlight what that concept is. For this one here, which alkene reacts the fastest with MCPBA? This is something you went over directly in class, but it's also something in general that you need to know, right? Like I mentioned, alkenes, right, are nucleophiles in their reactions, and so really what we care about is their pi density. How much electrons do they have, right? Because electrons are going to dictate how well they react with electrophiles, right? The more electrons you have, the faster reacting your alkene is going to be. Okay, in these electrophilic additions, right? So this could have really been almost all the electrophiles, right? It wouldn't have mattered except for one of them, right? We'll go over the one that's kind of the exception. So which electrophile does the alkene react the fastest? Now, like I mentioned, EDGs, right, increase the rate of reaction, and a popular type of EDG with alkenes is the R group, right, a carbon chain. So in terms of substitution, right, increasing substitution is increasing rate of reaction, right? So whether we have, so these are usually about the same, right? Because they're all disub. And then we have the trisub. Then we have the tetrasub. Okay. So for 99% of alkene reactions, right, the more sub the alkene, the faster it reacts first, right? So if we look at this, right, the most sub alkene is this one here, is tetra, right? This is di, this is terminal, or it's geminal really, so it's di. And this is tri, right? But this is tetra, so it's absolutely the best. Okay, so most electrophiles, fastest reaction is going to be with the most sub. Okay, the one electrophile where this is an exception is going to be the BH3 electrophile because it's so big, right? It's so big it always wants to go less sub. So in this case, right, we would actually go with Well, we have to go with the less subalkene for BH3. That would be either one of these two, but there is a better answer to both of these. If you think about it for a second, which one is less sterically hindering, right? Look at this. This has a CH2N, this terminal, so this would actually be the best one for BH3. Okay, so for most electrophiles like MCPBA, this is the answer here, the most sub, right? But BH3, it's a bit bulky, right? So it's going to go with that as less sterically hindering, as least sterically hindering position as possible. Okay, cool. So that's how that question can be asked and how you can kind of put a twist on it, right? Ask it in a different way. But again, remember nucleophiles, right? So also then that means that groups like oxygens that donate electron density into pi bonds react faster than anything because they are so juiced up, right, in these electrophilic additions. And again, things with like ketones on them where they withdraw pi density, make them less nucleophilic, react the slowest. Cool. All right. So that's that trend there. So again, MCPBA will be this answer. BH3 will be this answer here. Cool. Which compound's the most polar? So I know a lot of you guys probably saw this question and instantly circled the cis isomer because you guys learned that CH3, right, donate in, then they have a net dipole down, right, with some canceling. If it were trans, right, you'd have one in, one going in this way, they both cancel out to 0. And that's okay to think, right? So it's okay to have instantly circled this. But remember, we're thinking about what is the effect of the group on the alkene, right? In general, right, halides will withdraw and R groups will donate, right? They'll donate into the carbonyl. So we're thinking about what do these effects do together, right? We're not thinking about just, what do we memorize in class? So in this first alkene here, we have a donation effect and a withdrawal effect, and both are in the same direction. So as of right now, this is the most powerful dipole because everything lines up, right? CH3 donates this way, CH3 donates this way, this cancels out, so it's 0, right? So nothing here. BH3 donates in, BH3, BR withdraws, and then CH3 donates in. So we have a little bit of canceling, but we do have a net dipole going this way, right? Although we do have a little bit of canceling, right? We have a up and a down, right? If you're good at vector math, right, you can just think this and then like this, right? So you can see that this is the net dipole, although there's a little bit of canceling. And then bromide takes out this way, bromide takes out this way, right? That is going to be a net cancel. Okay. So yes, there is a dipole here, but there's a little bit of canceling, right? Because we have that their vertical vertices are canceling out. So in fact, actually, it's going to be this guy here that is the highest in dipole. It has the highest dipole for sure. Okay. So always be considering that for these questions. This is where people get tricked off. Okay. They always mess up this part. Okay. So remember that halides withdraw, carbons donate. And that's how we determine, and we add them up, and that's how we determine which one's the best. Okay, cool. Which compound's most acidic? So we're looking for a hydrogen that's acidic. Remember that for carbons, when we think of sp3 carbon, so sp3 carbon, sp2 carbon, sp carbon, right? Or I should say, so spch, sp2ch2 and sp3ch3 kind of, right? Or I guess I'll just put ch here, right? The order of acidity is this way. This is acidity, so this is base acidity. So if I have like an alkane, right? I have an alkene and I have an alkyne, right? The order of acidity would be this is 1, this is, or I'll put it here. This is 1, this is 2, this is 3, right? That's the order of acidity. So you can kind of order that goes, guys, as such. The amine NH, right? Where does that fall into? It falls right here. Okay. So amine is going to fall right here. Okay. So I think a lot of people might accidentally do this, circle that instantly, right? And think, oh, that's the most acidic. That would be the case if this were H, right? That would definitely be the case. That's the most acidic. But that was the trick of the question, right? There is no alkyne H. There is an sp3H, but there's no alkyne H. So in fact, right, all we have are these sp2, right? This is technically sp2, and you'll learn why in 118C, or I guess a little bit later in 118B. This is definitely sp3 or sp2, I guess, but NH2 is what's going to win here, right? Because there's no sp alkyne proton. So this is the winner. Okay, cool. Another way this question usually asks is order, like rank the order of acidity. So rank the order of acidity here. Now, this is particularly hard the way I've written it, but I guess a better way to have written this question was if there's no like double bonds in here, because this ring makes things a little, I mean, it's a benzene ring. If you guys haven't learned already, that thing makes things a little bit weird. So if I wanted to rank the acidities, right, these would be probably really close, but the presence of the alkyne could stabilize an anion here, right, because it's electronegative. So this would be more acidic than this one. So in terms of least acidic, this would be least acidic, right? Followed up by this dude here would be next up and less acidic. If we were to just consider this alkene proton here, it's actually, you know, I wish there was I should have done a better job with this problem. But let's say we were only looking at the alkene, right? At the alkene proton, right? This proton here would be next up, right? And now this would be first, okay? So not the best problem for ranking because there's some other things you guys don't know yet that could affect this. But general idea is what we could write here. Okay, cool. All right. Question's a popular one. You'll see it on all the midterms almost. I asked this question. Cool. Which atom is involved in sp2 and sp bonding? So, I mean, the key phrase here is the sp2 and the sp. Sp is what we're looking for, right? If we can find the sp bonded atom, we probably found the answer. So any atom with 2 pi bonds, right? So 2 pi bonds. This has no pi bonds. This has 1 pi bond. This has 1 pi bond. This has 2 pi bonds. So it's this atom here. This is actually a very old problem. I mean, you probably saw it in Gen Chem or saw it in 118A. You're seeing it now again. Okay. This is known as an allene carbon, or this whole structure is an allene, but that's the allene sp carbon. It actually has a very cool bonding instance where we have a pi bond that's going vertical and then a pi bond that's going horizontal, kind of. Okay. So actually the R groups for an allene, we have horizontal R groups, right? So ones that are going in and out of the page, and then we have vertical R groups. So ones that are going up and down. That's the chemical makeup of an allene. Kind of interesting. Cool. Again, nomenclature, just figure it out. But let's get into the products, right? Been waiting for this one, right? So hopefully for those of you that didn't need the review, just come to here quickly. Okay, cool. So hopefully now for those of you that need the review, you can get through some of these very quickly. Like, we don't have to do these in order. Some of these we can, just look at and know exactly. Like this here, right? That's always a concoction for the carbene, right? The dichlorocarbene. So we know that it's going to make a triangle like that. That's all it does, right? This here could be wedged. So possibly we could have a dashed answer as well. The cool thing is that if you draw 2 answers, if they're identical, you don't get docked for them. So if you weren't sure and you just drew these 2 answers, you wouldn't get docked. But you could get docked if you wrote racemic here because you demonstrate you don't understand what that term means if this is not chiral. So if you're not sure, right? Because I'm actually, I'm not sure. I'm pretty sure it is, but just in case if I weren't sure, right? That's something I could do to make sure. Okay, cool. So I'm gonna go ahead. I'm gonna go ahead and put this like this because we can just put that there. Okay, pretty cool, right? That's pretty simple. If I look at this here, an alkyne, where I have Br2 CCl4, we talked about that, right? Alkynes, very quickly, we said that alkynes, if we add Br2 to them, right, we're just going to add 4 times, right? Especially in excess, we'll add 4 times those bromides. Now, technically, we could have stopped here. Oops, sorry. Right, we could have stopped at the mono addition, like I had drawn, right, which will appear to be technically anti, right? That would be at 1 EQ, but very rarely is that question ever asked, but it could have been, right? So at 1 EQ, we could have stopped there, right? That's a possibility, okay? MCPBA, right? That's a simple one. We know that turns this into a triangle with an oxygen on it. And then again, the NaCN is just going to crack open on one or, more or less, depending on acid or base. Very, very good rule of thumb. If you don't see H+ in that step, it's not acidic, right? This is going to be basic. I don't know why I said acidic like that, but it's going to be basic. So NaCN opens on this side. Okay. Now remember the OH could have been wedge or dash. So, that's going to make this racemic. Or, at the very least, is going to make it look like this. So I'll include both. That to me is I'm more comfortable doing that. Okay. Here's a good question. Let's say that I had both sides equal like this, right? And I added in NaCN. Both sides are equal. So technically acid or base shouldn't matter here, but maybe one side is better than the other. Right? What do you guys think? Was it going to attack on the A side or the B side? Okay. The answer is we always have attack on the B side. Okay. Always. And the reason why is because terp-butyl, again, that's sterics. Why would you choose to attack steric side? We could attack less steric side, right? Absolutely no reason. Absolutely no reason. Now, again, OH and CN, because we went through a triangle, should be anti to each other. So I could have an OH that's wedge and a CN that's dash, or, right, OH that's dash, CN that's wedge. So in this case, that's a possibility. Okay, cool. Pretty cool reaction if you ask me, right? All right. What other ones can we quickly do that just don't take it very long? Oh, look at that. We have lithium NH3. Lithium is just like Na solid. We talked about that's the reaction that turns alkynes into transalkynes. So looks like we have 1, 2. So 1, 2. And then we have 1, 2, 2. So we have the transalkyne there. And then we have the OSO4 reaction, right? That's the dihydroxylation reaction. So that will just put 2 OHs here that are syn to each other. Super simple. Okay, cool. So those are ones that you can do very quickly, or I mean, they're really just, you know, recalling reactions. The rest of these are a little more like, you have to think about it a little more, like a little more nuanced. For example, we have a ring alkoxide. Remember what I said? You see an alkoxide, you want to think E2 elimination, right? So with the ring, remember, always make sure that there is antiprotons on all possible sides, or on all possible beta carbons. Beta carbons being this one, and this one, right? On this beta carbon, I have a dash H. On this one, I have a dash H, and this one will have 3 H's, so it doesn't matter. So I can do eliminations on either of those carbons as long as I have the base that can do it, right? I have a small base here, a ethoxide, so I'll probably eliminate on this side here. So I'll get this alkene here. But imagine if I did like terbutoxide, right? Terbutoxide would have eliminated on this carbon here, so I would have had this here. Unfortunately, this guy never really wins in the elimination game, unfortunately. Okay, cool. All right, so that one, got to think about a little bit, but it's not too bad. Looks like we have H here. We have an elimination because we have, again, alkoxide, and we have, looks like a very suggestively drawn bromide. Remember, we can do a trick here. Whenever the H and the Br are syn, what I can do in this elimination is just draw out what I see and then just switch one side. So I can just switch that side there and I get my alkene. I could also rotate too. That's also possible. I'll just go ahead and rotate the bromine side. Right. So bromine I want in the back, so I want it there. That pushes the H to the front, or like to the plane, and then the methyl to the front, like that. Okay. And then I can do my elimination here as well if I wanted to, but you can still kind of see it still follows that pattern of making this here. Okay. So you got to do what you got to do. Do what you got to do. Right. I just, you know, wrote this problem so it'd be easy to use a trick. Okay. But you got to think about it a little bit, right? You got to think about it a little bit. Now, let's say that I use the bulky base, right? Again, that's why it's always important to scan the base real quick, right? Let's say I use an LDA here, right? My betas are this carbon and this carbon, right? Looks like my bulky base would just give me this alkene here. Right, I just get that alkene there. So cool. All right. By the way, all these extra examples that I go over will be in the key. Like I'll add them at the end. It's not like you have to have been watching or looking at this. They'll be in the end anyways. Okay. So don't feel like you need to copy everything down at the pace that I'm doing it. I need to speed up because this is hitting the 2-hour mark and I only have like about half an hour left that I want to go up to this. Okay, cool. E, we have H plus in heat and alcohol. So that to me suggests dehydration. Again, always draw the cation, folks, because look at this. Drawing the cation indicates to me that, hey, I can do a methyl shift. Right? If you don't draw the cation, that's harder to see. Right? So I get this, and the elimination occur here. So many times I see people fall for this one, and they draw this here, and it's so sad. It makes me cry. Please draw the cation for these, and you'll never get these wrong. Okay, cool. If I have this one here, I do a couple steps here, but I can remember HBr ROR, usually one equivalent. We'll have the bromide on the left sub position because it's ROR. We can add Mg to insert here. And remember, Grignards react with carbonyls, and that next step is this particular carbonyl. It's an aldehyde. So what I will get is the addition of this molecule here. Oops, sorry. This molecule here. Okay, cool. So those predicted products, hopefully they were not too bad. I mean, the first two midterms, I made sure they were mostly recall with a little bit of concept in them, not too crazy. But 8 problems is not a lot, right? I mean, over the 4 midterms, that's 32 problems. You could use more. So one thing you guys can do, and it really, requires you to do more studying too, but you can take these molecules I've given you and do other reactions on them, right? Like who says that it has to be these reactions? There's literally a million reactions you can do. You just gotta think and write them. So for example, this one here, what if instead I did MCPBA, right? That would give me the triangle oxygen, the epoxide. And then maybe I do conditions where I react to open up on the more sub, so maybe, or less sub. So maybe I do like CN here, or I do a reaction condition that opens up on the more sub. So like an alcohol in acid or something, right? Again, I'll write these out on the key as well. But again, do other reactions on these so that you can see what happens, right? So you can assess what is going to be the product. So you get the practice of doing it, right? No one ever said that it had to be those things. Like what if I did here CH2I2, right? And zinc copper. Again, this is not the most fun reaction, but it just forms a triangle. That's cool. What if I did Br2 H2O, right? That would give me OH on the more sub, Br on the less sub, right? That's exactly what I would get there. I could even do, I'll do one more before I move on to the others, but maybe I do, I don't know, like OSO4 or something, right? They'll give me the, well, that's not very important. That's not very fun because that's not, it's not a fun one. What's a fun one? Oh, maybe I do O3, right? And I make these 2 products here, right? Cutting down that middle of the pi bond. Don't forget with the MCPBA reaction, right? That's you'll make that organic side product, the carboxylic acid looks like this. Okay, so take these and do 2 more reactions, right? Like just choose whatever you want and just do those 2 reactions and see what happens, right? For example, what if I just got rid of these and all I did was NaNH2? So minus here, because NaH2 deprotonates that proton. And then I add in the CH3CHO, right? Well, hey, guess what? I'm going to get this here instead. Right? So that's what I'm going to get instead, right? What if I did, instead of HBr ROR, what if I did 1 equivalent HBr so that I get this bromide here? Yeah, I guess you could even stop it there. I mean, you could do the Mg and continue, and you'll see, oh, that just means that I'll form the alcohol here, right? I'll get the alcohol there instead, right? If I now then do my step 2 and 3 that I already had written down originally. So instead of doing the HBr ROR reaction, right? Things to consider. Let's say here I did Lindlar's, which now gives me the cis-alkene, right? And now I do the OSO4 reaction. That's going to be a bit of a different answer there, right? As opposed to the other one. Okay, I could do any reaction I wanted to. Maybe I do MCPBA, right? MCPBA would just give me that. Okay, so that's how you expand the number of reactions you can do, and to show yourself what it is that's possible. I'll be doing that with the other midterms too, and I'll I'll throw them on the key. But that's just, again, that's how you do that. I mean, that's what we kind of did with this one here. We consider what a bigger base would do. Same thing with H, right? What a bigger base would do. So cool. One thing I'll mention though with the so I didn't really go over this, but asymmetric alkynes, whenever you do a reaction like excess like HCl, you always get 2 answers because you don't know where the Cl is going to add since it's both are disub. So you'll form a diCl product like this, but you'll also form a diCl product like this because you don't know where it's going to go, right? You don't know where it's going to go, whether it goes to the right or the left, right? Same thing if you did a 1 equivalent type reaction, right? You'll just go either here or it'll go on the other side, right? Like Cl will add here. Okay. And then there won't be on there. So like this, right? Anyways, I'll write these on, like these will be on the key anyways. Okay, cool. All right, so pick the products. How can we add more to that? Cool. All right. Or mechanism. So mechanism questions, you usually got to guess the product. That's because the philosophy of that is that you can write whatever product you want, and as long as you have some mechanism towards it, you can get partial credit. If you were given an answer here and you had even 1 incorrect step, the TAs would have to dock you like a lot. So I don't know, whatever. Usually the reactions are not too terrible, just in the predicted product. So we just cut down the middle there. And we get these two here. We can also go through the mechanism of this one. Mechanism is pretty, I know this one looks weird, but it's basically two reactions back to back. So it's a crown reaction. Okay, so it's a crown reaction, which means that we're just going to get, so O- attacks here. That's an attack back. We get this there. And what we form is I believe the malazonide. I believe that's the first term, is malazonide. Don't worry about, I know this is trans. Don't worry about where these methyls show up, or ethyl, sorry. It won't matter in the grand scheme of things. But this here is what we call a 1,3 dipolar cycloaddition. Okay. Why is it called that? Because the ozone reagent is a 1,3 dipolar reagent. Okay, that's just what we call it, and it's reacting with the alkene, through orbitals to make the cycle. So this is a 1,3 dipolar cycloaddition. Okay, and the cool thing about this is that once you do this, this is actually very, very unstable. You can imagine, because of the 3 oxygen bonds, or like the 3 oxygens right next to each other. So this will actually decompose, and it'll decompose as such. Okay. It actually doesn't matter how you draw these, as long as you show some kind of decomposition arrows. But if you follow like the way that I'm doing them, wait, hold up. This goes here like that. Yeah. If you follow the way I'm doing it, basically, right, this bond here becomes a carbonyl with this oxygen. You break this bond between these two oxygens. So now this is a completely separate molecule, but these guys will still be bonded together, and you'll have this here. Okay. So these are our two reagents. This is what we call a retro 1,3 dipolar. Okay, so retro 1,3 dipolar. Okay, and all it does is it recreates a dipolar reagent that we can now then use to do another 1,3 dipolar. The only thing here, though, is that we have to flip over the carbonyl that's not the dipolar reagent. So I've got to flip this guy over, and it should make sense why. We want the minus to attack the carbon, not the oxygen. Okay, but we can go ahead and do another 1,3 dipolar. And in this case, right, you'll always make this shape here. Okay, this is known as a malazonide. So this should, yeah, this should be malazonide. Or wait, is this malazonide or shoot? Even I'm forgetting. I actually think this is the ozonide. I apologize. I think this is the malazonide. The terms don't really make sense, right? So it's like, I mean, even I mess it up all the time. Let me just quickly check. Yeah, the first one's malazonide, the second one's ozonide, but the ozonide is this is the shape of it. It's like this, two oxygens bond together, then carbon, then to an oxygen, right? Then we have these here. This is relatively stable. Sorry, it's relatively stable until we add in like a reducing agent. In this class, it's like usually sulfur is the guy that does it. The sulfur, for reasons that again are unknown to you guys, it's really attracted to oxygen. So what'll happen is the oxygen will be attacked, and then this guy will use one of its bond to attack the sulfur there. But now this is just going to decompose. We're going to do this and this. Okay. It doesn't matter if you attack this oxygen or this one. It really doesn't matter, as long as you attack one of them. And you break it such that one bond forms a carbonyl and the other one forms a carbonyl. Oh, sorry, no. There we go. That's better. So, let's do this then. So how can we always get this right? So let's say I attack this oxygen here. You break the OO bond onto either side here. It does not matter. So I can do it here or I can do it here. It does not matter. I'll just do it here. And then that bond there is just going to break over here. Does that work? No, that doesn't. What? So if I break this here, am I overthinking this? Oh, I am. Sorry. There we go. So sorry, let's go through this again. I was overthinking it. Oxygen, right? Sulfur takes the oxygen. This is the bond that breaks here. So it'll break here, right? And then we'll break this one over here. Oh, I know what I'm doing wrong. Jesus. Sorry, it's been a long day. Sorry, let me just reset. So once again, how can we always do this right and not mess up like I have goddamn million times now? The sulfur is going to attack the oxygen, okay? And then the OO bond, just have it attack the sulfur, okay? Just always do this. Always use this OO bond to attack the sulfur, right? By doing so, right, now you can just decompose this very simply. You can either decompose this where this bond breaks here and this bond breaks here, okay? So your choice. Or you can, well, actually, I guess we'd have to do it that way. Because the other way work? Yeah, I guess the other way could work too. So we just want to make two carbonyls, right? So we'll break this bond here. We'll break this one here. Okay. I think if you go with this way, it's just always safer. So use the OO bond to break this bond to attack the sulfur. Okay, sulfur will attack this oxygen back, and then we'll form a carbonyl here and form a carbonyl here. And now, finally, after a million mistakes later, we get our two carbonyls. Okay, cool. There we go. There's the ozonide. Not too bad. I mean, again, it's just the two reactions the same, and then the reduction step. Not too crazy. Okay, cool. All right, so that's that reaction there. And again, mechanism, you can practice with any of them. Just do any of them right now, right? That's the easy thing to do. Cool. All right. Now, synthesis. So I do want to take some time to go through the synthesis, although we don't have enough time, as much time as we had before. But I do want to go over some synthetic tips for synthesis, just because that's my domain, right? That's like, that's what I know. So again, with the alkene, the biggest thing is going to be the vicinal difunctionality, right? This thing here. If there is an X and a Y anywhere in a molecule next to each other, it indicates to you that that came from an alkene, right? That's the biggest indicator of an alkene. So your job in synthesis is to just figure out what X and Y are, right? And define that in these molecules, right? You could start with a lot of easy practice, like with Br and OH, right? Obviously, right, this came from, breaking that, and it came from like OH and Br. How do we add OH and Br? It's a Br2 and water, right? Stuff like that. Some of the more crazier examples are the rings, right? Like if you have something like this, right? Not kind of hard to see, but hey, that's a O and a Br right there. So my vicinal functionality is right here. That's my pi bond, right? And I'll have this, so Br2OH, right? So allowing that to guide you, or to at least help you out, is what's really going to help you. Knowing old reactions will help you too, like, because you can obviously your head TA or professor can write the question such that the functional was transformed. So one of the most common transformations is, let's say I do an epoxide reaction, right? One of the most common things you'll see is the epoxide's opened with something like OR, and then it's oxidized the alcohol, right? So now suddenly it's not very clearly an epoxide, but it's just an oxidized version of it. Okay, cool. So things like that, right? So obviously carbonyl oxidations are facilitated by chromium reagents on alcohols, and alcohol, remember, alcohol vicinality, that's always a very good clue of the epoxide, where the alcohol is the epoxide O, and then this is just the reagent that opened it up, right? That's a very good one to know. Most functionalities, vicinal functionalities, are going to come from, very obvious reagents. Like if you ended off with a di-OH, right? Obviously that's going to come from either an OSO4 or from like an MCPBA opened with water, right? I guess the stereochemistry will matter there, right? If it's a syn addition, then it's going to be OSO4. If it's anti-addition, it's going to be that. Okay. So yes, a big part of this is knowing your reactions, but at the very least, you can start to guess if you know your vicinal functionalities, right? Alkynes make things very easy, because if you see a bunch of things being added to a single carbon, or even to, vicinally to a carbon, it's super obvious where it came from, right? Like the tetra halide is obviously the alkyne. The gem dihalide, obviously the alkyne. Ketones and aldehydes, right? Especially this here, if you see like a bromoketone, that is 100% yelling at you in your face what that is. But yeah, so access to these, knowing which functionalities are accessible. The other thing about the alkyne is that Grignard thing we talked about, right? So here, the fact that we can extend carbon chains with alkynes. This means that if you ever have the ability to do so, you should try to use an alkyne to make some carbon chain. That's always a possibility. Okay. Cool. Well, anyways, I think maybe the best way to do this is to just start doing problems, and we can talk about them afterwards. But yeah, cool. So hopefully you guys tried these. I'll just kind of walk through my thought process here. Again, I kind of see where the vicinal difunctionality is. It's CN and COH, right? Carbon chain wise, pretty much the same. So I think nothing too crazy there. But I'm thinking this is just the Jones, right? Just to simplify that, that's just a Jones. And so now I have a CN with an OH. Again, vicinal difunctionality, OH, I'm convinced this is an epoxide, right? Where this is the epoxide O. So CN added on these two carbons, the more sub. So this is not going to be NaCN, it's going to be HCN. HCN is going to crack this epoxide open. Another way to write this is NaCN HCl. But anyways, now we just have to figure out how we make this epoxide. That could have came from an alkene, MCPBA, or you could have done the Br2 H2O, right, into NaH. That works too. Either one. And then from here to here, this 118B class is going to be absolutely in love with Br2HV. Anytime you start from an alkane, you probably want to use that. And then this is just an elimination, right? I have 2 beta hydrogens I want to eliminate on the left sub. So I want to use terbietoxide. Okay, cool. So look at that. I use sound disconnection theory, and I'm able to really easily come back to my product. It's not too bad at all. Okay, cool. All right. So this is a very simple synthesis, and it's indicative of a very useful one, and one that's seen a lot. Ways that this can be riffed up and changed up is usually from the epoxide. You can open up, let's say, on the left sub side, let's say like that, and then I could do an oxidation to get something like this. So the alpha cyanoketone, right? That's one way you can change this up. I suppose what you could have done is, what else could we have done here? Other functional groups, I guess. So like if I had like another OH here, maybe. Nah, that would kind of suck, to be honest. Yeah, not much else, right? Once the epoxide, really, I mean, I guess the real big thing is adding like an ether, something like that. Or if I open it up the other way, right? So this is the basic opening. This is the acidic opening. Try to see if you can reason why. And then we could do something like this, right? So instead of having the CN there, we have the ether. So all possibilities, right? All things we can do. Cool. So that's how you kind of riff with synthesis problems, right? You just kind of just replace reactions, see what they would make. If there's ever a way to reverse this activity, you try to do that. Okay. But again, that idea that the alkene, right, gives you control over 2 carbons, right? Just look for where those 2 carbons are, right? Actually, we can even talk about this. Let's say that what we ended with was this here, right? Let's say we ended with this here, where we only have 1 functionality, right? A lot of people have a hard time when there isn't 2 functionalities to look for, to figure out how to get from, this alkene to this here. Well, remember, we can also add H. So if you ever have 1 functionality, right, imagine H could be the other functionality, and we can think, oh, okay, that's a terminal alcohol, primary alcohol. That's how we use BH3 for that. Okay, so ways to find these functionalities, and ways that these can change, right? Nothing too crazy, right? I mentioned, so there is one thing I do want to talk about. There's a synthetic trick, or little thing you can consider. So let's say that we wanted to go from here. I recommend you guys try this. We go from here. I guess it would have to actually be this to here. Okay. So I kind of talked about this in the review, but consider this, right? So pause and try it. Hopefully you did. If I try to do Br2HV here, it might have been some of you like, oh, I can cheese this. This is not going to work, right? Remember, bromine loves going to tertiary positions. So we can start with this, but for sure not going to work in one step. But I can brominate here. And let's consider how an alkene would help us, right? When I look at my end product, I see a bromide. And again, I don't see anything vicinal. So not really the most useful thing here. But I could imagine that there's 2 hydrogens here. One of them could have been the vicinality, right? So H here could be my vicinality. So bromine and hydrogen. I could have added HBr across this pi bond. And so what that makes me think then is that, okay, I did HBr here, but I added it in a way that Br adds to the less sub. So it must be the peroxide version. So I could, one thing that I always say when people are stuck on stuff like this, like they can't see this, I always say, what sound does a line make? Right. So let's really, really badly draw a line really quickly. The hell does a line look like? I don't even know. Right. Maybe something like that. I don't know. This looks really bad. But that's a line there, I guess. But what sound does a lion make, right? It roars. So we can use roar here to get that reverse selectivity. Okay. And then, right, from this alkene, right, considering from this bromide, right, how can we track this alkene over? Well, if I were to eliminate, I kind of have two options. I could either make this alkene here with the bulky base, not going to help me. I could also make this alkene here, which can help me, right? Because this alkene is kind of snaking towards the end like that. So I could just use a small base for that, right? How could we get to this alkene here, right? How can I promote a bromide formation so that I could make this alkene here? Or even an alcohol, I guess not an alcohol actually, but a bromide, right? Well, we could do another ROOR reaction and then do a bulky base elimination. Okay. So this is a little thing I call kinetic walking, right? And it's just the idea that if I wanted to snake the alkene out to a less substituted position, a less stable position, I'd have to use some combination of ROOR and terbutoxide or LDA, right? To get the less sub hydrobromination and then elimination to less sub position. Okay. Now guess what? If I just wanted to go back to the more sub position, super simple. H plus in heat, right? That will allow my alkene to isomerize super, super simply. Right, no doubt about that. Not stressed about that at all. Okay, so cool little technique there. Cool. All right, so we'll call it on that one. Move on to the next one. So we're starting with this bromide, and we're ending with this alcohol that clearly has more carbons. I can kind of trace over that. It looks like we have these 5 carbons here, and then we are adding in these 2 carbons here. Okay, but recall that, anytime we add a new carbon chain, especially with an alcohol, that's a very good indicator of a Grignard. So I can cut here and say, okay, I had a Grignard reagent here. And then this alcohol is either a carbonyl or it is an epoxide. Easiest way to tell is if when you cut it, the alcohol is right next to the cut, right? It's usually a carbonyl. I guess the other thing you can do is you can put a positive where you cut, and if it's next to the oxygen, it's a carbonyl. So we added this aldehyde into this, this Grignard. If it were one more down, so if it were like over here, right? So now that when I cut it, the alcohol is 1 over from where I cut, that's an epoxide. Okay, so a little synthetic tip there. Okay, but this is my Grignard, and Grignards are just made by adding the magnesium to the bromide. This here. And so now I have to ask myself the question, how do I make this vinyl bromide? Right? Where have I seen this before? Maybe I erroneously wrote a predictive products question that actually has the exact sequence. Okay. I didn't realize this, my bad. But anyways, to make this vinyl bromide, right, that's just one equivalent addition of HBr, right, to an alkyne. But keep in mind that the alkyne, if I did this, would give me the bromide that forms this way. Right. I want the bromide that's on the opposite, that's on the less sub end. So I use ROOR. Right. And then from, to make alkynes, terminal alkynes, right? That's from an alkene. That's just Br2. And then excess NaNH2. In synthesis, you can always just put excess NaNH2. That'll always be fine. Like, who cares if it works or not, right? Just remember to put the water work up afterwards. Okay. And then this from this is just LDA or some bulky base. Okay, cool. So again, using sound disconnection theory can help you out a lot. I have the other midterms pulled up here. I'm not going to talk explicitly about their syntheses, but just looking at them, right? I want you guys to consider, again, vicidal dysfunctionality. And what does that tell you? For example, this synthesis here looks like a typo, right? It looks like I made a mistake, doesn't it? Because we have this here, this here. It's like, what's going on, man? Like, it looks like I made a mistake, but I didn't, right? But we can help simplify this by considering, okay, dibromo, that's where my alkene used to be, right? And then from there, I can start to brainstorm about things that I can do here, right? For example, right, looks like my carbon chain is just kind of randomly changing, right? It's turning from a 3-carbon to, or 2-carbon, 3-carbon to a 4-carbon, right? It's almost like I reset the carbon chain, right? I use the new one. Trying to give you guys a little bit of hints of what kind of reaction you can use here. There's a type of reaction that we keep erroneously, like people keep teaching erroneously that if you lose carbons, this is the reaction you want to use. But I don't think that at all. I think the better way to think about this reaction is that it's a reset on the reaction. Actually, you know what? Screw it. We'll just talk about it. So what is this reaction that I'm doing that's allowing us to create this new carbon chain that looks like we're functionalizing this end carbon here? Well, if I'm kind of renewing this carbon chain, what I'm saying essentially is I'm ditching it. I'm getting rid of it, right? And how do we get rid of carbon bonds? In this class, the only way to do it is the ozonolysis, okay? So I actually should have made this a little bit shorter, but so I apologize. This will make this a bromide. This is a PBr3 reaction, just a reminder of that. You will need to know that for synthesis, by the way. But I can eliminate here. Okay, so I can eliminate here with like I mean, it's a more sub versus less sub, so terbutoxide again. And then I can do an ozonolysis, okay, which will give me this here. And so ozonolysis, again, chops off the chain in a sense that I'm resetting it, right? I'm getting rid of it because maybe I don't want it, right? Because I'm trying to change it. And then I can do a Grignard here that adds in those 3 new carbons, right? So I'll get an alcohol here. And then guess what? I have what I need. We'll have to turn this alcohol into a bromide because we need to eliminate, right? We need to eliminate on this position here. If I did elimination from here, right, I would get this alkene here, which is not what I want, right? That would ruin everything. I don't want that alkene. But I do want the alkene that goes where those dibromos are, right? So I'd have this, right? Go from here to here, again, terbutoxide, and then Br2, right? CCl4, okay? So again, what's the point of the synthesis other than, you might think, oh, you just wanted to show off, you wanted to make this hard. It's not that I wanted to do that. I mean, yes, I do like writing hard problems and showing them how easy they are because everyone can do them, right? But the point here is for you to rethink what ozonolysis really is, right? For far too long, right, it's been taught ozonolysis is the bond cutting reaction. It's a reaction that loses you carbons. That is true. But you have to think of it as it's also possible to reset a carbon chain, right? Because you essentially said, okay, I don't like this carbon chain. Let me cut off most of it and I can add in more because I'm given the aldehyde. And the aldehyde can directly go towards adding a new chain, right? And so that's what I've achieved here. I'd be surprised if someone could think of a faster way of doing this. 1, 2, 3, 4, 5, 6, 7. Oops, that should not have been that long. I apologize. I don't know why that was so long. But I would be surprised if someone thinks of a faster way of doing this. It'd be pretty cool if you could. It'd be a nice one. Okay. Cool. So yes, there was a Grignard involved, but maybe not possibly the Grignard you thought. Because I mean, I guess the way to think about it is, if we're going to add carbons, it has to be near functionality, right? If I'm adding a carbon, like if, it looks like I'm adding a carbon here, there is no functionality here, right? I have to let the functionality guide me, right? So how could I do this from a retrosynthetic standpoint instead of that kind of forward that I did where I knew the answer, right? Well, again, I see that first off, I can get back to here, right? At the very least, right? So I can get back to there, right? Br2. And then I think to myself, okay, I'm clearly adding in a new carbon here, right? But I mean, if I look at where that new carbon is being added, it's kind of remote. It's not near any functionality. So rather than erroneously thinking that I'm adding in one new carbon, I have to think I'm adding in multiple new carbons and around functionality. So instead of saying one new carbon is being added, maybe I'm adding 2 new carbons because it is next to this bromide, right? Or I guess in this case, next to this alkene, right? Maybe these 2 carbons here are being added in, right? So potentially I can imagine, okay, if this is a Grignard, then this here must have been some kind of alcohol carbon, right? That's got to be some point there because again, Grignards have to add to carbonyls, right? I could try to retro this a little bit and say, okay, I could add a carbonyl here, but you'll kind of notice very quickly that this one gets a little difficult because you've got to, you got to make this aldehyde somehow. which I guess then you can kind of see, oh, I went from 3 carbons to 2. So actually, hold on. Maybe we can do something here. Maybe I did not. Maybe I had some retrosynthetic blindness here. Let's say this was Br, and I turn this into. Oh yeah, actually, it works out almost exactly how I would have wanted it, I suppose. But I could have got this. Oh, actually, no. So this is where this fails, right? It's because I could have eliminated here, but in order to get this aldehyde here with the one less carbon, right, my alkene would have had to have been out here, and there's no way to drive selectivity, right? There's no way to drive the alkene out there. If I do HBr ROR, I don't know if it goes here or here, right? So I can walk myself back this pathway, right? Notice that, okay, I think this new 2 carbon chain is being added next to functionality. And that leads me back to this aldehyde that's clearly lost a carbon, so it's ozonolysis, right? But I can see that adding OH here isn't what's helpful, right? It's not helping me out here. So let's consider if the OH were on the other carbon. And this is where we can kind of break, I mean, this is the breakthrough, right? Add the OH here and then say that all of this was added in. Did I miss a carbon? I'm not sure. Anyways, we can say that all of that was added in. And so suddenly now, oh my God, right? Oh yeah, I'm missing a carbon. So now this is our Grignard reagent, right? And again, we see the ozonolysis, and then we can kind of see how it matches up now, right? I want to form the alkene here, and I want to ozonolysis that off, right? Cool. So difficult question, but again, to kind of reconfigure your thinking of how these reactions work, and at least a way to kind of walk yourself through these. Okay. And maybe, hey, who knows what? Maybe I'll ask a question that's going to be asked on the exam, and you'll just get that for free, right? That'd be cool. Cool. Just because we're on it, I'll even do this one too. Alkyne to this. Again, if I think about transformations, 3 carbons, I may not be sure exactly which 3 carbons are here. I've seen a lot of people use a lot of different ways of doing this, but always let functionality guide you, right? I see this OH here, so I'm almost convinced that one of these 2 carbons is the alkyne carbon, and I'm gonna go out on a limb and say this one is 2. So, I mean, for the most part, I tried to line these up so that they would be like this. So I'm allowing the alcohol functionality to guide me and give me some advice here. So I can see that I've essentially added in 2 carbons here. I've added in this methyl and this ethyl piece. Okay. I can imagine maybe in some kind of Grignard way. But again, if I kind of look at this and I think about, okay, where in the world did this alcohol come from, right? I can maybe start to think about vicinal difunctionality, right? Because if I'm convinced that these 2 carbons here are maybe these 2 carbons here, because, alcohol dictates functionality, right? But what's the other functionality here, right? I have an OH and I have carbon chains, right? What's the functionality that I'm looking for, right? What am I considering is the thing that is vicinal to my alcohol? Because if I can figure out what's vicinal to my alcohol, well, hey, guess what? Right? I can have said that was an epoxide, and my nucleophile could have opened up to give me this alcohol. Okay. So what's my vicinal group, right? I have an H, I have a CH3, and I have an ethyl. What could I use? This is the hidden vicinality, right? This is the hard one. This is like how sometimes it's, sometimes you have to look at a primary bromide or a primary alcohol and see that H next door and think, oh, that's a hydroboration. So what's the trick here, right? The trick here is realizing that this carbon chain is your vicinal functionality, or even this one, right? So either one of them could have been it, but I'll do the correct answer and I'll tell you why this is more correct than the CH3. Okay. So the trick is realizing that this guy here is your vicinal functionality. Okay. And you're adding in essentially a Grignard reagent, right, to open that up. So alcohol, and then looking over here, right, I had these 2 new, so these are my original carbons, right? Looking over here to see these 2 new carbon chains. One of those carbon chains is going to be my Grignard nucleophile, okay? And then from here, it's fairly simple, right? We do the alkene. From here, it's the alkene. And then from alkene to alkyne, right, that would just be, it doesn't matter which hydrogenation you do. You can do H2PD, or you can do the the NH3. This is just MCPVA or BR2, right? NaH if you wanted to, right? Now it's just a matter of adding in the CH3, right? Because we went from 3 carbon to 4 carbon. Terminal alkynes are very good at alkylations, right? So we just do NH2, and then you can do BCH3, BRCH3 if you wanted to, right? But terminal alkynes, right, they can add functionality to them. So actually some of the best questions are ones that give you an alkyne and then just ask you to make something from them, right? So something like this, right? Where you're just kind of alkylating on both sides here, and then you're just hydrogenating and then epoxidating, right? Stuff like that. So cool. All right. So why is it that I went with the ethyl as the nucleophile and not the methyl? Well, if I draw the epoxide, that's the result of adding a methyl. I would have this methyl ethyl epoxide. CH3 minus when it attacks does not have a clear reason to attack either here or here. If anything, it might attack on the methyl side because it's less steric. So this might even lead to the wrong stereoselectivity. When I have the dimethyl, it's actually it's symmetric, right? It's not asymmetric. So green could attack here or here, it wouldn't have mattered. Okay, it would be giving the right answer. Okay, cool. So a little bit of that hidden dye functionality. So midterm 2 syntheses were it kind of bumped up, I would say, opposed to the syntheses on this side here. So yeah, I mean, these are, what you would expect from this professor, right? This is the level of understanding. And I think it's a fair level of understanding. You just have to be confident in yourself and see these transformations. Okay, cool. All right, so those are the syntheses. That's all I want to talk about there. I want to kind of wrap this up. I think we hit 2 hours now. So let's kind of wrap this up. Let's get into the NMR section. Again, there's 3 other exams with 3 other keys that I got to make, right? So I'll probably get done with 2 and 3 tomorrow. No, 2 tonight and then 3 tomorrow. That's probably what'll happen. Okay, because again, this one was more review, right? This is midterm 1. Cool. All right. Anyways, elucidating structure. What can we do here? NMR, always a bit difficult, but there's a couple things that you just need to know. Generally speaking, on the NMR, going to the left increases in electronegativity, increases in de-shielding proton character. So some ranges to kind of know, about like 5 to 6-ish. This is what we call the C double bond C H region, so the alkene region. So if there's an alkene H, so an H on an alkene, that's where we usually see these guys. So actually, let me do it this way. Yeah, there's like H's on an alkene, right? That's where we'll see them. From about 3 to 4, what you'll usually see around here is like halides next to oxygen, next to nitrogen, right? These CHs here. Okay. From 2 to 3. Oh, sorry. Let me use a different color here. So CH, CH, and CH. From 2 to 3 is where you see allyl protons or alpha protons. So these are guys that are next to pi bonds. So next to an alkene, next to a carbonyl, next to an alkyne. And the alkyne proton itself also shows up in this region as well. Okay. Everything below this is boring. So these are just normal alkanes. Usually around 4 to 5 is where we see like protons that are flanked by 2 electronegative groups. Okay. So if there's something that's like really highly de-shielded, it can't be just next to oxygen or just next to nitrogen or just next to halide. It's usually next to 2 of them, is the case there. For these protons here, the OH and the NH, these guys are variable, but they show up as broad peaks. So you don't have to really guess. You'll just know. You'll just see them. Okay. Other peaks that are good to know is down here at like 9. If there's like a triplet or like a singlet, usually some kind of like, proton here. That's a 1H. That's usually an aldehyde proton. Okay. If it's down at like 13, that's a carboxylic acid proton. Okay. And that should be pretty much good. That should be good enough for this. So screenshot this if you need it. That's like your guideline, your little tricks, tips and tricks. Okay. For the CNMR, all you really need to know is that around 200 is where you see ketones and aldehydes. So to confirm that they are there, use the CNMR. How do you tell the difference between the two? This and the HNMR, right? Just look for that. From 160 to 140 is where you see esters, carboxylic acids, and amides, right? Usually these guys here. So this answers the decade-old question of how do I tell the difference between a ketone and an ester? You use the CNMR because ketones show up 200, esters show up around not 140. It's like 160 to 180. So here, that's where these guys will show up. So that's the decade-old question, 180 to 160. So no, there is no one of these guys in this question. That was a mistake. Okay, cool. That's all you really need to know. Alkynes tend to show up around 60 to 80, around here usually. And then C double bond Cs show up from 100 to 150-ish. Okay, cool. That's all you need to know. All right. So with that, we should be able to solve this one fairly quickly, I suppose. Or at least get fragments down. So you can always do DOU first. That's like a point usually. So 7 times 2 equals 14 plus 2 equals 16. 16 minus 8 is going to be 8 divided by 2 is 4 degrees. Okay. One little thing that you've probably been told before is that there's 4 degrees. Look in the NMR to see if there is a benzene ring. If you benzene ring NMR activity will be 7 to 8, but we don't even have an 8, so there's no benzene in here. So we've got to have a combination of a lot of things. Things we can think of, 4 degrees can be a lot of things, right? It can be like 4 double bonds. It could be 4 rings. It could be like 2 rings and a double bond. Triple bond could be involved in a double bond and a double bond, right? Again, this is why it's, this is why CNMR is so important. It can help you decide between which ones are which. So when I look in here, I see activity 60 to 80. I'm convinced that this might be some kind of alkyne. So I'll write down an alkyne as 2 of my degrees right there. I see an alkene. Alkenes and alkynes come in pairs. Okay, so remember that they come in pairs. So that means that if you're going to have either one of them, there should be 2 lines per each functionality. So I think that there's also an alkene in here. You can also see that there's this huge separation on the alkene, right? So there's some kind of electron effect going on where one is super shielded, one is super deshielded. We'll go over that in a second. But other than that, I don't really see any other functionality, right? I mean, you might be convinced that that could also be an alkyne, but even if it were, right, that's 2, 4, and then 5, that's too many. Whenever you have a degree that can't be resolved in the CNMR, it's usually a ring. So it looks like we're gonna have a triple bond, a double bond, and a ring involved in this. Okay. So I can even start to think about that. Usual rule of thumb is I look at the formula. If it's like, I usually subtract 2, and I see if that gives me a ring size that I can work with. Because I mean, like, think about it. It's not gonna be a 7-membered ring, right? Because we have CH3s, we have a bunch of CHs. We need to be able to, like, turn these things into this. And also there's a triple bond, right? So triple bonds can't be inside rings, unfortunately. So for sure, at least 2 carbons are outside of the ring. So I'll start with 5 as the size of my ring. If that doesn't work, I'll move to 6. Okay. But I also have an oxygen in this formula. Okay. And this oxygen, if I kind of look in here, I kind of, trying to figure out if it's in a carbonyl, if it's in a, alcohol. Carbonyl, I would have known if I looked in the CNMR, right? They would have been activity 160, 180, or 200. So no carbonyl. Alcohol would have had some kind of broad 1H, right? Broad 1H singlet. So you usually have like a 1H singlet. That's an alcohol. So it's neither of those. So this is some kind of ether. So I'm going to go ahead and make a guess that this is going to be a cyclic ether, right? And it could be a 5-membered. It could be a 6-membered. I guess we could start with maybe the 6-membered first, right? Just to kind of get that out of the way. And if I kind of think about what proton is probably next to this oxygen, it's probably going to be, I mean, if there's 2 protons next to it, it's probably going to be some of the more deshielded protons. So obviously the 5 to 6 is reserved for the C double bond C. So we'll look at that later, but possibly these 2 could be right next to my my oxygen ether. So I can go ahead and try this. So looks like we have a 1H pentet. So that means that there's going to be, so 2 neighbors there, and then possibly 2 neighbors here, possibly. Okay. And then we have, looks like a 1H triplet. So that would be like 1 here and then 2 there. So maybe something like that. So I mean, just for the most part, I'm just kind of writing things in. Actually, immediately now I know that the structure can't work. Okay. So how do I know the structure can't work? Well, if I look at my carbon count, 1, 2, 3, 4, 5, 6, 7, I've exhausted all carbons and I haven't even gotten my alkyne onto here. And even if I could get my alkyne onto here, right? If I put an alkene on any of these carbons, right? I mean, I can't put alkenes on this carbon because I need that 1H there. And if I put it on here, I can't have the 2 H's that I've been counting as neighbors. So already this is contradictory, this 6-membered ring. It's not going to work. Okay. 6-membered ring is not going to work at all. So now I want to move over to the 5-membered ring and try the same thing over again, right? Where I say, okay, I think that there is possibly, for sure I know this 1H pentat is gonna be next to the oxygen, right? That I'm convinced of that. So that would mean that you would need, right, 2 neighbors there, and then potentially, 2 others here, right? So we could have 2 other neighbors there. I'll just kind of put, I'm not sure exactly what's there just quite yet. Okay. So we need 4 neighbors. I could also start to think about the alkene, right? Again, these are alkene protons. Here's a really good tip, right? If you see 2 alkene protons, it's probably a transalkene. If you see 3 in this area, it's probably terminal, right? So the difference is just in trans, you can't tell without coupling constants. And in this class, you don't really do that. But you can tell the difference between terminal and trans because it's 2 versus 3. So I know there's some kind of like, transalkene, although actually in a ring, it'd have to be cis. So I think that there's a, alkene in this ring. Again, if I'm going with the idea that these 2 are neighbors, I can't put the pi bond there and I can't put it there. So the only place left is to put it here. Okay. So I'll put that there. And then I looks like I have a 1H doublet of doublets and a 1H doublet. So these are just really fancy terms for, doublet just means that it only has 1 neighbor. So I can imagine if I had these 2 protons here, this guy here has 1 neighbor. Doublet of doublets is a fancy way of saying triplet. So looks like this guy's just tripleting with something else. Looks like this guy's a triplet actually. So if this guy's a triplet, then that means that I can't have 2 H's here actually, right? Because it's a triplet. So it's going to be partner there and a partner there, only one of them. So that means that this has to be a 1H, okay? Which makes this really interesting now, because that means that if this here is a pentet, then 1 neighbor here, 3 have to be on this side. So I've got to go ahead and put the CH3 here. I imagine some of you probably figured that out earlier and were probably screaming through the screen. Anyways, cool. So I can get that there. All that's left now is my alkyne. I just throw that on there, just like that. Okay, cool. So that's my NMR. This one was a little tricky actually. This one was probably a little too hard. One little tip that I'll teach you guys. So what are some tricks that you can help figure these things out? So the alkene range is around 5 to 7. And usually alkene protons really stack next to each other, like really, really close. Like this is actually interesting separation. And we also saw that down here too, right? The alkene carbons are incredibly separated. Whenever you see alkene protons that are separated on the lower end of this range, so another way of seeing this is the 100 to 150. If you ever see one carbon that's really high up and one that's really low, this is the indicator that we have some kind of pi donator in the system. Because if I look at this pi bond here, right, the oxygen donates, what I get is a minus charge on that carbon farthest away from the oxygen. So electrons are going to shield the crap out of this carbon. It's going to really, really shield it. And that's this guy here. It's all the way at 5. That's how badly it's being shielded. And then we have a cationic oxygen next to this carbon here. So this hydrogen is being incredibly deshielded because it's almost like an aldehyde. It's almost like an aldehyde proton, right? So it's pushing up really, really high. Okay. So resonance effects can really, really affect pi density. And this is also the case in, if you have a withdrawing group as well, right? Let's say I had this guy here and I have a, resonance effect, which it would be this one here, right? Carbonyls next to pi bonds will force the closer carbon to be super shielded. So usually around like 6, and the other one to be super deshielded, usually around like 7. Okay. There is an example of this in these practice midterms. Okay. So that's one pattern you can look out for, and it'll instantly tell you, whether you have a conjugation. If there isn't this present, this kind of polarization, usually these protons are right next to each other. They're on top of each other. And you'll see patterns of that. Okay, cool. All right. So that one was actually a bit hard. I apologize. It's okay if you didn't get that, but hopefully you got some of the fragments like the ring, the triple bond, the pi bond that's disub, the DOU. That would have gotten you at least like half the points, right? In this one here, we can kind of see again, these 2 alkene protons, alkene carbons are close, and you can even see here that they're really close, right? 6, 7. So probably not anything too crazy, although actually it is separate. Usually these are a bit closer. So I think, is there a carbonyl? Yeah, there is. Look, 200, right? Ketone or aldehyde. I don't think it's an aldehyde. So I haven't even done the DOU, but I already know there's a ketone. And I do see I mean, this is a pretty big separation, 6 and 7, right? It's 1 ppm. So if I wanted to Hail Mary this, I will. I'll say that this is conjugated, right? Because again, ketones conjugated to alkenes will cause this. And I mean, well, this one here is gonna be really shielded. It's a doublet. It's a doublet. I don't know why I put DD there. That should just say doublet. We have a 1H, it's a multiplet, so there's gonna be a 1H here, and it's deshielded, so that makes sense. How many neighbors that has, I'm not entirely sure, but I'm willing to guess that, I mean, there's a 2H, 2H, and a 3H, okay? One of these 2H's is all the way up at 4, so that's probably next to our alcohol that we see here. And then we also have this guy here that's closer up to, to 3. Remember that if we have a proton that's alpha to some pi bond like alpha, so it's like right next door like this, right? That would be up next to 3. So I think that there's a 2H here possibly. Although 3 is pretty high, I think maybe this one at 2 is better. So I'll put this one here instead. Okay, just reasoning myself through, right? This is just next to a pi bond, right? It's not on it. So I think it'll be this 3H here. That just leaves this 2H, 2H here that would have to go here. And then so the alcohol would have to go here. Yeah, that works. That works. I think that should be the correct answer. Okay, cool. I didn't even do the DOU. I just kind of looked at CNMR to do that. Okay, cool. I know there's a bit of like bias because it's like I kind of have an idea what the answer should be. So I know what to look for. And also I'm like, I think running like 2 hours into this. I kind of want to end this. So, I'll post up the NMR video that I made again. It kind of goes over the basics and what you need to know. You should be fine. There's actually one I made for 118B. I'll send that actually. There's one I made for 118B. So I'll send that for the NMR. You guys should be good. Cool. All right. With that, that's midterm 1. Hopefully you find that helpful. Again, this is the longest one because we went through a review. The other 3, I hope you can hear me snapping. Just going to be going through it. So that last hour that we did, that's basically what these are going to be. Yeah, because again, this was mostly supposed to be a review. Cool. All right. So any questions? Anything that looked weird or I might have messed up? Probably did. 2 hours in, I'm like really tired. So let me know. Have a good one, guys. See ya.